Good afternoon, everybody. Thanks for coming back after lunch. My name's Gurarie. I'm a professor at the State University of New York College of Environmental Science and Forestry. As usual, the longer the name, the smaller the institution. I've been doing movement analysis for a while. I have been to an AniMove once before, and that was 10 years ago. Incredibly, in Virginia, in a place somewhat similar to this. And that's practically where I first met Chris and other people, and Kami, etc. So anyways, it's a pleasure to be here. And it's exciting to talk about movement data and how to analyze it and how to think about it. And in particular, to encounter people from all over the world with all your fascinating creatures. That's just the best. So anyways, I'm very excited to be here. And I really thank the organizers for having me here. We had a little bit of a few exchanges. So they're like, oh, you teach segmentation on day 2 or whatever in the morning. And I was like, well, I'll teach segmentation, but only if I can talk about movement models. And then I was like, well, and we've tried that, or we don't, or maybe that's not how we do things a certain way. And then I was like, well, I think the best way to segment, to understand what you're doing, whatever you're doing, doesn't matter what you're doing. And this holds for everything. So the messages have been very consistent. It's fun to have different people teach, but the messages are very consistent. So a lot of the things that were pointed out this morning when it comes to modeling is you just have to understand. You don't expect there to be a magic bullet, right? But the important thing is to understand what you're doing and why you're doing it, right? So what is actually going on? And so with that is a little bit of background. And I will say also that some of the things I did want to talk about were sort of taken up this morning, which is great, because then I feel less bad about taking all sorts of things that Chris probably wants to talk about tomorrow, right now. So it all comes around. So let's just talk about, and also we were told earlier, I didn't get the memo, this was not a statistics class. You're going to see a little bit of stats, and it's just important not to worry about the equations necessarily, but just understand what we mean by a parameter, a process, a distribution. And I'll try to make it as illustrative and clear as possible, and please, ask questions at any moment. Movement models. Okay, so we're going to start with basically, there's discrete movement models, there's continuous time movement models. We're going to start with discrete movement models, right? And so I guess I wasn't here yesterday for class. I was just recovering from jet lag, and standing in lines in Switzerland and stuff. But presumably you talk about steps, you talk about turning angles, things like that, right? And then there's just the fact that a lot of you are collecting data or working with data that's been collected. And data, there's like X, there's Y, and a location, and that's an observation. And there's like a whole row of them, and that's discrete. There's a whole bunch of little discrete observations. So your data are kind of discrete. And so the main, maybe most intuitive paradigms for modeling movement data are also discrete. And there's a lot of pedigree behind discrete movement models. But let's just talk with the absolute simplest model. This is a movement model, I guess. We can call this 1D, discrete time white noise. And this is very familiar to you, or should be very familiar to you. This is just every observation is an independent normal variable, right? And this is just in one dimension. So we're talking one dimension here. So okay, bouncing around, all right? This is what every time you run a linear regression, you have this assumption of IID residuals. Hopefully that's not totally foreign to you. You're talking about an assumption of normality, right? And so what are the properties of this process? Well, the properties of this process are basically, the important ones are that it never escapes too far from 0, and it has a variance. So the mean of this process, in this case, is 0. Maybe there's an actual mean that's non-zero. And the variance of it is sigma squared. So the variance is this measure of the spread of this process, right? Okay, that's 1D white noise, and you can also have 2D white noise. Right? And so 2D white noise means that's the process that's happening in the x-axis, and that's what's happening in the y-axis. Every location is sort of independent, and it kind of bounces around like this. Okay? And I'll just point you to this particular kind of a figure because I use it a lot, because I find it extremely useful for looking at movement data. And that is, you have x and y here, sort of a trajectory, and then you have what's happening in the x and what's happening in the y. This is not a very interesting one, but it'll get more interesting. Okay? And there's a property, there's some statistical properties to this very simple model, and one is that the mean distance, for example, from the mean can be calculated, but basically it's just constrained here around 0. Okay, so this is like a 2D discrete white noise process. All right. The next sort of thing, and this seems very similar, but it's qualitatively quite different, is the random walk. Now, the random walk is basically the sum of a bunch of white noise processes, right? So here it's not the location, which is random, right? It's the displacement that's random. And then you sum up all those displacements and you have a random walk, okay? So this is sort of the model here, right? So we call it RW, maybe in one dimension. XT is XT minus 1, that should be minus 1, plus some white noise. It also has one parameter, okay? So this thing can also be in 2 dimensions, right? So this is like your 2-dimensional random walk, right? So every step is sort of an independent random thing, but you keep adding up those steps, you keep adding up those steps, you keep adding up those steps. And this thing has some slightly different properties. Let's see, I don't have those there. But basically, nothing is constraining this guy. So all of a sudden, we've lost any spatial constraint. The expected value of this process is, well, the expectation is that the average expectation is that it's at 0, but the actual, over time, the distance that it travels is infinite. And that's a very important property. There's other sort of properties that are just good to think about, because again, this is sort of the simplest, one of the simplest, I guess the second simplest discrete time random process. And one is that the step lengths are composed of the square root of the sum of 2 random normal variables, and that has a known distribution. It's called a chi distribution. So if you just looked at those step lengths, right, see a distribution, it's unimodal, it's skewed, right, and that's kind of like what most step lengths will look like in general. And then, sort of by definition, the turning angles will be uniformly distributed. Okay, you can, this sort of thing that kind of we like to do as much as possible is we have a process. This process has only one parameter, this sigma, but we can measure something. We can look at this like histogram of the distributions of step lengths, and out of that distribution of step lengths, we can then estimate that parameter, right? By using this, the mean step length, the mean of this will be the square root of 2 times sigma, because math. Okay, so that can be handy. Things like that. Okay. Now let's talk about an autoregressive process. Okay. Now here again, we're going to start with one dimension. This right here says that your location at time t is going to be your location at the previous time. Again, sorry, those plus 1s should all be minus 1s. At the previous location times a little number that pulls you a little bit closer to 0 plus some random noise. So every time you get away, you keep getting sucked back to 0. Every time you go away, you keep getting pulled back to 0. Okay? That's what an autoregressive process is, right? And it has 2 parameters. This first order autoregression coefficient, autocorrelation coefficient phi, which is between 0 and 1. And again, that same sigma that we put in everywhere. Okay? Now this thing can't escape, right? It can't escape 0. And so it has sort of a known variance over time, right? That saturates. And this autocorrelation function, which was so nicely introduced to you and which you played with and you've all run, this ACF command, very quick, simple command. It shows you that the autocorrelation function, that there is sort of significant autocorrelation. Okay? Now, in 2 dimensions, we can have this sort of like 2-dimensional autoregressive walk, right? So now we have this thing where in x and in y we have this sort of, it's trying to leave, but it can never quite leave. It's trying to leave, it can never quite leave. Okay? And there's, this is again, it's beginning to look maybe a little bit more like animal movement. A little bit. We're very, very slowly trying to become a little more realistic. Important to note in this 2D autocorrelated random walk? Well, one thing is that there are things that you can estimate, that you can predict. If you know the parameters, you can kind of predict that area, the 95% area, for example, using this kind of handy formula. Very simple, right? Or alternatively, if you have the area and you want to kind of predict, estimate your phi's and your sigmas, then you can use that as a clue, right? And then important to know that in locations, there is autocorrelation. So if we just look at the autocorrelation just in one of the dimensions, x or y, it's autocorrelated, right? Because the x and the y are each these one-dimensional AR1 processes. But the steps are not autocorrelated, right? So each step is sort of in its own independent step. Okay? All right. So those are like a couple of discrete random walk, discrete time movement models. Those are all legitimate movement models, right? A model is basically us saying that we don't know everything, so we have to summarize things statistically. With some statistic, we can kind of describe this process. And so far, there have been 1 or 2 parameter models, right? The correlated random walk is maybe the most commonly used in a way or fitted model. And it basically can be summarized as your location at time t. Okay, good, I got a -1 in here. Your previous location plus a step. That's it, right? And then that step is described by some angular distribution, right? So a very common one that I like a lot is the wrapped Cauchy distribution. The reason I like the wrapped Cauchy distribution, it's a distribution, so it has a parameter, it has a shape. It's wrapped. Have you seen these Rose diagrams before? Do you guys know what we're looking at here? Okay, it's pretty intuitive, right? So like you're more likely to be going zeros to the right here. We like thinking in terms of radians. So zeros to the right and pi is behind you. Zeros forward, and you're like more likely to go forward than backwards, but there's some probability of going backwards too. Right? It's a continuous wrap distribution. The reason I like the wrap Cauchy distribution is that there's one parameter in there. If you ignore the mean will just always set at 0. The one parameter is that clustering parameter. If that parameter is 0, it's a uniform distribution, so that's a random walk, total random walk. And if it's 1, then you're always going straight. And one nice thing about that, again, because we like estimating parameters, is that if you take an unbiased, good point estimate of that coefficient is the mean of the cosine of the turning angles. So if you're always going straight, the cosine of 0, you might remember with trigonometry, is 1. So the mean of all those 1s becomes 1. And then if you're all over the place, then the mean will be on average 0. So it's very easy to estimate. And then you have some distribution. All right, so then we have the step distribution. And this is just a very empirical thing, right? You're just like, okay, well, we'll pick one that works. You can use a gamma distribution. You can use a viable distribution, some distribution that has a couple of parameters, right? So now we have a model that has 3 parameters. Basically, that clustering coefficient and then like these 2 parameters that describe the steps. And I do want to note that the correlated random walk, I think the first time literature was used in this kind of classic paper by Gurarie and Shigzada. And unlike you all with your fancy devices and GPS data, what they were looking at was butterflies moving from flower to flower. And so their discretization was not this arbitrary discretization that comes from data. It came from the fact that the butterfly was on a flower, and this is kind of like nice sounding fieldwork too, and they just followed the butterfly, and they would draw on their little notepad where the butterfly was going. And they noticed that the butterfly tended to keep flying in the same direction. And that is a very kind of interesting and good use of the correlated random walk because it is an actual discrete process. There are movements and there are stops, movements and stops. Okay, easy enough to simulate in R. And I will notice that this model 2 has no spatial constraints. It just moves on forever and ever and ever, much like the random walk, because there's nothing to pull it back to 0. But that the steps themselves are not correlated. So it has this name, correlated random walk, but you have to really think about what is actually correlated in there. And what's correlated in there is just the turning angles in a way. You can think about it sort of, although the turning angles themselves are sort of independent, they just come out of this distribution. Right? So the whole movement is sort of autocorrelated, but a random walk would also have been correlated. Anyways, it's a little bit imprecise as a term, and like there's nothing in that correlated random walk movement that says that the steps themselves are autocorrelated, for example. Okay, so are there any questions about that correlated random walk? Okay, so we're going to talk about, not just talk, we're going to go ahead and fit this multi-state correlated random walk later this afternoon, if you bear with me. But we should, I want to introduce it because this paper came out in 2004, extracting more of relocation data, building movement models and mixtures of random walks. And and I would say, in a way, I would say in a very concrete way, this is one of the most influential papers in that absolutely countless amount of analysis of animal movement really follows almost exactly the steps that Pájaro, that's the nickname of Juan Manuel Morales from Argentina, used in this particular analysis. And basically he was like, well, if you look at these elk moving, in particular in the winter, they're cratering and they're feeding, or they're moving to a different patch and they're eating, they're moving, they're doing something else, they're moving, they're doing different stuff. We have locations, right? And so let's just sort of describe their movements as having two states, or maybe three states. One he called encamped, the other he called exploratory. And these are sort of the turning angle and the step length distributions. And so there's this behavior that's exploratory, has longer steps, and much more clustered turning angles. And then we have this encamped state where you're basically just bouncing around in one particular area, right? And so in that model, you have your two parameters for your step lengths, you have your parameter for your turning angles, right? But you have two sets of those, right? And then there's this question of, well, how do you switch between those states, and why do you switch between those states? For that, I'm just going to do a brief aside, again, because all this sort of jargon notation and words are very important, fundamental. So I'm going to talk about what is a Markov chain. Right? So I don't know, is that a familiar term? Have you heard of Markov chains before? So in what context? For behavioral segmentation, mainly for that. Okay. Yeah. The idea, maybe you've also heard of MCMC. We've been exposed to MCMC, and so MCMC stands for Markov Chain Monte Carlo, and that is a way to estimate parameters in the Bayesian framework. But there's what is this Markov chain thing? What is a Markov chain, right? And a Markov chain is a model. It's basically a model for, say, it's a discrete time model for transitioning between states, okay? And if you have, for example, three states, A, B, and C, the model is entirely summed up in the probabilities, in these probabilities of transitioning, right? So these probabilities of transitioning from one state to another state, PAB, B back to A, you have all these probabilities. At any given moment, if you're in one state, you must go to another state. It could be the same state, but you have to go somewhere. So the sum of the probabilities leaving one of these guys has to be 1, okay? And so there's just there's a little matrix of probabilities that encapsulates the whole thing, all right? And we write that matrix in terms of a probability transition matrix, right? So from, to, and the rows of all of these have to be equal to 1. So it looks like there's 9 parameters in here. There's actually only 6, because the last one's sort of fixed by the other 3. And one thing about this, just the only other thing, I don't know if, the one thing about Markov chains to keep in mind is that for a majority of relevant Markov chains, there is going to be a stationary probability distribution of states. right? And stationary is kind of misleading. And I like thinking about, for example, tossing a frisbee or kicking a football, right? If you and two of your friends are maybe passing football back and forth, you have the ball, maybe someone's closer to you or you like them more, you tend to kick the ball more to them, and they have some probability of kicking it to somebody else, and they have some probability of kicking it back to you. The ball is always moving. It's always moving between these states. In that case, it doesn't even stay in the same state ever at each step, right? But then over time, the stationary distribution will be like, well, I end up, because I'm always passing it to my friend, and she's passing it to me half the time, I end up having the ball way more than the person over there has the ball. So you can have different distributions, and that stationary state is kind of the end product of this Markov process, carried over and over and over and over again, right? So just to give an example, and I just threw a little bit of R code here as to how do you do this. Let's say you have kind of a three-state movement process. For example, you're either chilling or you're cruising or you're huffing, right? And we don't know what state you're in, right? But you're kind of switching between these three states, okay? So chilling, you're like not moving that much. Cruising, you're kind of sort of moving. And huffing, you're moving a lot. If this is the probability transition matrix, right? This is a realization of a Markov chain. I guess the only definition of a Markov chain or Markov process is that your next state depends only on their previous state. And then, you get this multi-state random walk. Here's like a three-state multi-state random walk, right? With that transition probability matrix, I can just sort of like run it forever and compute how much time it's spending in each of these. Or I can take the matrix and solve the matrix, essentially, and you get the same thing. So this particular creature spends half its time chilling, 35% of its time cruising, and 15% of its time huffing. So, and again, this is all a little bit so you understand the context of these hidden Markov models. What does it mean to have a hidden Markov model? We refer to hidden Markov models. I mean, they're hidden because we don't know the state of the animal. We don't even know. The state is also a model, right? You're all making assumptions, right? But in any case, you don't observe the state. What you observe is how it behaves as a function of that state. And so you have to infer that state, those state probabilities. But and I know there's no context today. That's not till Thursday, right? No environmental context. But in 2004, Pájaro also modeled those transition probabilities as functions of covariates, right? So again, this is just so you understand what this fundamental model is. Every single one of those transition probabilities, right? It wasn't about what the behavior is under different elevations or snow cover or anything like that. It was under what conditions am I more likely to switch, like give up on my little crater here and start looking for another place? Or under what conditions will I stop looking around and start cratering as an elk, right? So it sounds crazy complicated, but, and for decades to do this, you'd have to basically write your own MCMC sampler, but there are now tools that are quite fast and quite easy. So we can do this afternoon, no problem. Fit multi-state random walk. Okay, any questions about any of that? Are there, just to get a sense, are there people that are interested in fitting hidden Markov models or behavioral? That's a yes and yes and yes and yes. Okay, all right. So we'll talk about how that's not too tough. Oops, sorry. Okay, so again, the discrete time movement models are dominant because your data are discrete. There's some tools that are very well developed for analyzing them. It's easy to say these are step lengths and these are turning angles. I hate the word step length, right? Because it's not a step. right? A step is a thing. A step is a biological step, right? Some processes are actually discrete. Those butterflies moving from flower to flower are discrete, right? But most of your steps that you're computing from your movement data are not steps. They're just like the interval, the spatial temporal interval between your sampling that you set based on price and device and technology, et cetera. Right? They're not taking those steps. Right? And then those parameters, okay, so you have some interval of time that you're like sampling these animals, right? And then you have this steps, and then you have like the parameters of the step distribution. What do those parameters actually mean? Right? What does the shape and scale of that step distribution parameter mean? Not very much. And even the clustering coefficient of the turning angle doesn't necessarily mean very much in discrete model, right? So, and again, I'm like maybe, I think it's useful to just see things presented from different perspectives. Some of this stuff, presumably, Chris is going to talk about tomorrow in Ines. But the basic, sort of the fundamental like argument for a continuous time movement model, which, you know, just spoiler alert, they shouldn't be like fetishized or anything. That's not the only way or the most important, necessarily the best way to model anything. But the real argument for them is that it's a model for a location at all times. That's another thing. Is okay, you have a correlated random walk model, and it says that, you know, every 4 hours this is my distribution. It doesn't tell you anything about where you might be in 2 hours. That's just another thing, right? So it's a model that tells you where a creature will be at any given time. So that's kind of nice. It's if you can estimate them, which is not trivial. They're kind of intrinsically robust to regular sampling, which depending on your system can be a really big deal. I started doing movement modeling with marine systems where in order for like this first seal or sea lion to like transmit a location, it has to be like on the surface, and the thing has to be working, and the thing has to be overhead. You know, like everything has to come together to get a location. So, you know, it's, you don't get anything remotely regular. We might look at some of those data. And also, the parameters and the estimates, they don't depend on that sampling scale. So again, if you took your data, you have 2-hour data, and you estimated all your like correlated random walk coefficients, they'd be completely different and not that easy, not trivial to relate to the same coefficients estimated at if you observe them every hour or every 5 minutes or something, right? And in principle, these estimates and parameters actually have biological meaning, right? So you estimate something like a mean speed. That's a real thing. Something like a ranging area. Some time scale of autocorrelation. Some characteristic time scale of movement. So those are sort of the advantages. The problem with the biggest disadvantage, of course, is that that all of them pretty much boil down to stochastic partial differential equations, which is like, I mean, it's hard enough to get a biologist excited about equations, much less differential equations, or partial differential equations, or stochastic partial differential equations. You're really like laying it on thick, right? So if I didn't lose you by stochastic, then you're not a biologist. They're not trivial to estimate. So we've already seen like pretty much every movement package, and you know, I don't usually use those kind of summary things, but most movement packages will immediately just give you the steps, right? And give you the turning angles, and like, all right, you go estimate whatever you want. They're harder to estimate, it's difficult to maybe add structure. It's a little bit harder to do that hidden Markov modeling sort of thing, for example. And then there's some strong, well, this is just always true, right? And again, this is like, there's many applications where you shouldn't use continuous time movement models, and you shouldn't believe, just because, so you can, you can get an estimate no matter what model you fit to anything. You'll get a number. You'll always get something, usually, right? I mean, if you can force it to give you a number. But what that number means doesn't mean anything at all, right? It's a huge question. And in order to like answer that question, you have to understand what you're modeling. You have to understand, you just have to understand everything. Right? That's where like the knowledge comes in, right? Your knowledge of the system and your understanding of what the model is fitting. So this is very true for continuous time movement models too. There are also strong assumptions, they're not all good. Okay, but let me just talk through a couple of them. And this is worth doing, I think, because these are kind of like the structural units of a model, right? So you can have a continuous time white noise, right? So just a quick note, before when I had discrete models, I would always have like z underscore t equals, maybe t minus 1 plus something. Here, you know immediately that it's continuous because there's like, it's in time is continuous and it's in a parenthesis, okay? Just notation-wise, right? It's a continuous model, right? So at any moment t, this is like a pretty uninteresting model. It's the white noise model, right? And so it's actually a completely psychotic model because it's saying that at any given location, it doesn't matter how quickly you sample, the next microsecond, the next hour, next day, the animal can be anywhere within this distribution, this normal distribution. Okay? But otherwise, it's the equivalent of a discrete time white noise. Right? So obviously, no creature does this. But that's the model, white noise. Okay? And then here, I guess maybe it's worth introducing the concept of the semi-variogram, and I'm kind of doing this a little bit to, I don't use semi-variograms very often because I don't need them most of the time for the main questions that they're asking. But they are useful for thinking about what these models are. And they're kind of central to certainly the AKD analysis and other CTMM things that you learn about. But basically, the semi-variogram tells you what is the variance of this process at a lag. Okay? At a lag. So the variance, again, it's like how different things are. Right? You have 2 points, right? So point now, point a microsecond ago, is it a small variance or is it a big variance? Okay? And this process is constrained in space, so the overall variance is just the overall, semi-variogram is going to be 2 sigma. But it gets there from 0 immediately to 2 sigma. Right? And why 0? Because the semi-variogram adds 0. The variance between yourself and yourself is 0. Right? Those are the same value. So all semi-variograms are going to start at 0, and then they're going to do something. And we're just going to pay attention to what they do for each of these models. So again, least interesting model, it's just immediately random, but constrained in space. Okay? All right. Brownian motion. Brownian motion. So remember we had the discrete white noise, then we had the random walk. And the random walk was just the sum of a bunch of sort of white noise steps. So this is sort of the same thing. Basically, the velocity is a white noise, and then we integrate that velocity. Integrating is the continuous time equivalent of adding steps, right? So this is completely random, and here's our sort of random walk bouncing around, okay? So this is Brownian motion. So it's like the cumulative sum of a bunch of infinitesimal little completely random steps. Basically, modeling this or predicting this with some equations is what got Einstein his Nobel Prize. So white noise, the one parameter in here is just the magnitude of randomness. It's still a 1 parameter process. What does the semi-variogram of Brownian motion do? So Brownian motion, much like that random walk, is unconstrained in space. It's going to move on very, very slowly. It's going to just eventually diffuse away, right? And you're close to where you were, right? But over time, you're going to get further and further away from where you were. And that's what the semi-variogram looks like. It just grows linearly with time. Okay? So all of these continuous movement models have direct counterparts to the discrete movement models that I talked about earlier. So, except that this OU position process is the direct equivalent of that autocorrelated random walk, not random walk, autocorrelated movement process, the 2D AR1 process I called it, right? But for some reason the OU position process is like a very important fundamental one, kind of in not just movement ecology, but like in stochastic differential equations. Like this equation is very well known and well analyzed, but people don't talk about a discrete equivalent of it. Anyways, the idea here is just very similar to the last one. So this is the integral of velocities here. You're adding up a whole bunch of little velocities. Here, we're also we have adding some random noise on top of this term here, which is giving us a rate at which we're coming back to a mean, right? So if tau is very, very large, if it's like infinity, then we're very, very, very slowly returning to a mean. If it's very small, then we're very quickly returning to this mean. Okay? So it's the equivalent of a discrete autoregression, right? Or a mean reversion process. Okay? Two-dimensional equivalent of this thing, right? So it looks like this. So it's also quite random, but it can't quite escape, right? And you could sample it, again, very, very highly. Your locations will generally kind of be close to where they were before, right? But it's always going to be being pulled back to the center. Okay? And I don't know why I don't have the formula here. But an important piece of this is that the only parameter here, again, is that it's like the magnitude. Well, there's two parameters. There's the magnitude of variation in the impulses, if you will. So like the variance inside of this W, and the other parameter is this time scale, the position time scale, tau p. So that tells you something about how much time it takes roughly to cover ground, right? So again, if it's very, very large, then you tend to hang around in one area, and then kind of slowly working your way back. And if it's very small, then you're just zipping around. So that's an Ornstein-Uhlenbeck position process in 2D. And you put that all together, and you can parameterize it in terms of this, the sigma inside of the W. That's very buried, or this alpha, I guess, here is very buried. But you can also write it in terms of just the area that this process covers. An area is something like a home ranging area, something that makes a lot of sense to people. So just here's an example. Here's 3 of these OU position processes with 3 different areas, a small one, a medium, a large one. And you can see that the semi-variogram before, you remember, it would either shoot up instantly and then asymptote, and then the other one went off to infinity. This kind of increases gradually and then asymptotes. So the semi-variogram is basically telling you that you're not running away. But at short time scales, it's quite linear. Okay? That's spatially constrained. Well-known process. It's basically the continuous time Ornstein-Uhlenbeck process in X and Y. This correlated velocity model we're kind of doing that thing again, where we're taking whatever process we had for position, but just forget that it's about position, and we're turning that into a velocity process, and then we're obtaining the locations, right? And so what we're doing here is we're saying that the velocity has this intrinsic autocorrelation, right? So if I was moving fast, then in a short time previously, I'm moving probably pretty similarly fast. If I'm moving slow, then the short time previously I was probably moving pretty slow. There's this autocorrelation in velocity. There should be a little v here, right? And then there's this white noise. And here I wrote this not as an alpha, but directly in terms of this little parameter nu, because that little parameter nu actually tells you the actual mean speed of this process, right? And then this is my speed model, is that Ornstein-Uhlenbeck thing, and then the location is just the integral of that. Okay? So this is the discrete analog, or the continuous analog, I should say, to the discrete correlated random walk. Typos. All right. How does it look? Well, you look at the velocity. The velocity is going to be kind of in the same location, coming down, and then we're going to add that up, and we're going to create a position, right? So that is what that correlated correlated velocity model looks like. Here's with a longer time scale. You can see how it just takes longer for that velocity to change, and then you integrate it, and you get this much, much smoother thing. Okay? And again, this thing, I was generate this thing with a known average actual speed of movement, right? And a known time scale of autocorrelation. Okay? Oh yeah, what's this? This will probably just, we'll just go and go and go and go. All right, time scales. All right. Once again, this thing is unconstrained. It's completely unconstrained in space. So in the long term, it looks just like the Brownian motion. So the sum of all the white noises, right, just went up linearly. But in the short time scale, there's a little bit of autocorrelation here. So at short lags, it takes a while for it to pick up. Okay? So this short time scale and the long time scale, there's nothing constraining it. If there's nothing constraining it, it's going to move on forever. But at short time scales, the variance is quite low. In the semi-variogram. Okay, so this correlated velocity model, and just I kind of worked with this model a little bit, dug up some old references, and it was sort of part of my PhD. And then it's kind of like I called it, and I was like playing with it and trying to fit it to things. And then I met Chris Fleming, who's sort of independently working more sort of on the location type place. And so this sort of fit into a little bit into kind of a larger unifying model, which you'll see shortly. But basically, I like to think of this as, if you do have high resolution data, as kind of like a nice fundamental unit of animal movement data. And if you can take a little piece of, you can take your trajectory and you can estimate the parameters, that's important. You can estimate the time scales and the mean speed, right? And then you might have different variations on that. I had this like unbiased correlated velocity model, or like this advective correlated velocity model, where you have this sort of like mean tendency that you're kind of a little bit correlatedly varying around in speed. You can have a rotational one. So this is an actual flight track of a kestrel in Spain. And it does this, it rises up on thermals and stuff, doing this circular stuff, right? And then drifts over, moves somewhere else, does something else. And you can have rotational, there's a lot of movements that are actually rotational, it's kind of fun. Rotational, advective, whatever. You can like do all these kind of elaborations, right? And then we can try to do this sort of segmentation also today, if we have time, of this particular like model. So I like to think of it as a kind of a fundamental unit of movement, right? Okay, the Orstein-Uhlenbeck F model. Basically, so now that you're kind of like used to these functions, right, you kind of see that this bit right here looks a little bit like that position, that OU process model, right? It looks exactly like the OU process model, except this impulse here, which was a white noise before, is now this velocity process. So we basically took this correlated velocity process and we put it inside of this positional process that kind of keeps it constrained in space. Okay? So this is what that looks like. It tries to leave, but it keeps getting pulled in. But on the short scale, it looks very continuous, right? So it really wants to leave, but it keeps being pulled back, right? And then it has this sort of like very continuous sort of variation in its velocity. So here's with a time scale of spatial autocorrelation, which is kind of, usually these spatial correlation timescales are much bigger than your velocity autocorrelation timescales. But you can see what it looks like if they're similar. Okay? So that is an Orstein-Uhlenbeck position model. And it does kind of, you guys, I could probably have quizzed you if you were paying attention. You would have told me that, okay, well, because at short term, this semi-variogram is dominated by that velocity autocorrelation, it's going to like have a slight parabola coming up here. But then in the long term, it's going to be constrained in space. And so the semi-variogram kind of, if it has both of those things happening, that's where this particular model comes up. And this is actually, I think, a diagram that, this looks like Chris's handwriting, I think. But anyways, that I think we sketched like in the last AniMove I was at 10 years ago, and took a picture of with the telephones of the day. And basically, there's autocorrelation in time, there's autocorrelation in space, right? If you have no autocorrelation in time, right? And you have no constraints in space, and you have a Brownian motion. What's that?
They're both temporal autocorrelation.
Yes, but there's a position one and there's a velocity one. Sorry, yeah, velocity and position, yeah, right. Yeah, they're both temporal allocations. Yeah, if you have no spatial constraints and no temporal autocorrelation, you have Brownian motion, right? If you have no temporal constraints, but you have autocorrelation in your velocities, you're like on this correlated velocity movement axis, right? And then if you have no autocorrelation velocities, but you are constrained in space by some time scale, then you're in that position OU process. And this sort of area is where you have some of both is this OUF. So those are some models. Any questions about this stuff? I'm going to show you in the next lecture, and maybe we can apply how we fit these, what it means to fit these, and why do we care about the models themselves. You don't always need to have a movement model to perform a segmentation, for example, but it can be useful. And again, one thing to reemphasize here is that, with the exception of the OUF, maybe to some extent, that the parameters that you estimate, if you estimate, fit this model, right? You fit this model, these different sections, right? Like this particular analysis of this kestrel, and it returns to you the speed at which it's flying at different times with confidence intervals. You know, that time scale of autocorrelation, if you care about that, you know, the rotational speed, right, with confidence intervals. So you actually get enough information that you could even use that as a foundation for simulating or exploring deeper or something. You have a completely, fully parametrized movement model, and that's kind of a nice thing to have. Can be useful. Not necessarily, but it can be. Yeah. No, I feel like it'll be jarring to just like fly right into the next lecture. Do you guys want to stand up and stretch a little bit? Drink some Shorla and water? Digest a little bit? Yeah. All right, let's do that. Yeah, welcome back. I want to, can you repeat your question for everybody?
Right, here. You had the question?
So I asked if we need to use this OF and OF semi-variogram and all of these models to combine or to identify the behavior states and to use the segmentation, like if we need to combine, verify before or...
Yeah, so basically, I guess the question is how does segmentation work with this whole OU-OUF framework? And the short answer is not really. They're kind of mainly the main applications of OUF. I'm going to show you some exceptions. I'm actually going to show you some exceptions. But the main applications of OUF is sort of to have a single model that characterizes basically home ranging behavior and accounting for a lot of detail about the movement. And I do, so it's a little bit separate than this, like, it takes a while to estimate these models. The reason it takes a while to estimate those models is because the complete model tells you that every location is kind of correlated to every location, every velocity is correlated to every velocity, right? So when you have, if statistically or just like computationally, you have a big matrix that's very full, and so you have to kind of figure out what those parameters are inside of this big matrix. So that's kind of like the short version. So it's a little bit too slow for something like a estimating states for a hidden Markov model where you're supposed to like be constantly sort of trying out different parameters and seeing what's happening and estimating all sorts of different things, right? It's just a little too slow for that. That said, there are a few applications where it's kind of useful. But I do want to point out one thing. sort of about the OUF, okay? And, not to be like super polemical about it, but it's like it's neat, it looks real, it's like correlated in velocities, and it's like spatially constrained like a lot of your data are, right? And do you know what this species is? So does anybody else know what the Myrmecophaga tridolacta is? Something about eating an ant with 3 toes. Yeah, so it's a giant ant here. And I was just at a workshop 3 weeks ago in Brazil, and there are a lot of people pulling in a lot of data, and they're really interested in basically home-ranging behavior against a bunch of variables, trophic levels, and like maybe ecotypes, and then sex and body size, all these covariates, sort of kind of meta-ecological analysis. And they're all like, okay, well, we have to fit, okay, it's all like OUF and AKDE. But what does the OUF model say? And again, this is why it's important to understand the model. The OUF model is saying that your velocities and your data are always like autocorrelated and we're spatially constrained. That's what that model says, right? And if you look at that, if you look at the behavior, the movement of this giant anteater, and this is typical. This is typical for definitely in Brazil where it's hot and you only move part of the day, right? You look at it, and this is like 20-minute data. There's like several months of data. If you actually look at it closely, right? So we're just going to zoom in for a little bit, right? This is not ultra autocorrelated velocity movement at all. Not even close. That's the wrong model. What the animal is actually doing, what most animals actually do, terrestrial animals at least, is they're in one place, and then they move over, and then they're in another place, and another place, and another place, and another place. That's why I say, I personally think that you have to kind of avoid the fetishization of these continuous time movement models. This is a very discrete process, right? And so I think the right way to actually, if you're actually really interested in modeling this animal, right? And when you ask the computer, which is the best model, it's always going to say OUF because you have so much high resolution data. But why? With like a really high timescale of autocorrelation, which is not real, because it's just not moving a lot of the time. And that's very different from constantly moving. So that's just a bit of a warning, right? There's a lot of information here. You don't need all this information for this animal. What you should do probably, if you really want to understand this animal, is identify the times when it's not moving and when it is moving. And like try to understand what is driving the movements between these like fixed locations, which are easy to pick out. It's easy to pick out. You only need an algorithm because there's a lot of data. But if you didn't have an algorithm, you'd be like, okay, it was there, it was there, it was there, it was there, it was there. So anyways, that's just a bit of a warning. So I was asked to talk about segmentation. I need to just make a public statement that I'm like hitting my jet lag wall right now. But we'll make it through. Segmentation, principles and pitfalls, right? Okay, so behaviors are always changing, and it can be important, it can be interesting to know where, when, and why, basically, right? And so there's been a lot of work sort of in the literature that goes into finding where and when, and if you're lucky, why a movement is changing its properties, right? But why the observed locations are reflecting, are they not reflecting a real change in behaviors? Okay? Broadly, you can call that segmentation, right? And then, so back in 2016, 2 papers came out that sort of reviewed, broadly, I would say reviewed or gave some conceptual framework. And there's a lot of tools, a lot of students have their data, and they're like, okay, what's my tool? What do I want to do this. Or the worst is when they're like, I want to apply this model, right? Never, ever say you want to fit a particular model, right? You should know what you want. You should be driven by the ecological question. You should use the tool that's appropriate to that question. Start with the question and your knowledge of the system, not with the model. It's a very common thing. So how do you choose the appropriate tool? So both of these papers are, I think, worth reading just for thinking about that. I should probably dump, I should maybe, is there a folder, a shared folder for just papers?
Yes.
Okay.
It's called readings in there.
Okay. So I'll dump things in there. But things are also evolving very quickly. So just going to talk about, you all did a wonderful job talking about first passage time today, and you've all fitted a first passage time. And the nice thing about first passage time is it's very simple, right? And it basically asks a question: how much time is it spending in the vicinity of every location? Right? How much time am I around every location? And then that can be used, and that in itself is not a segmentation, but very often, these aren't great examples, these are just from the original papers on albatrosses. But very often out of that, you get a very clear sense of what when they're shifting from the sort of spatially intense behavior to this less spatially intense behavior. All these questions about picking a radius, all this stuff, but I don't think it's not a drawback that you have to work with and tune and select the knobs for an analysis, because it's in the selection of those knobs that is your opportunity to use your knowledge, which is significant. You know a lot, use that. Okay, so anyways, first passage time is an example. I'm a little bit showing you, I want to just talk about a few sort of tools here that to make a point that I made in that 2016 paper. So the other one that I looked at, sort of in a comparison, sort of a comparative approach, was this Levier segmentation. Levier segmentation is sort of an old statistical tool, basically, which uses likelihood-based approaches to take a one-dimensional time series, so like speed here, this is a dolphin moving from here to here, and sort of find phases at which either the mean or the mean invariance of this normally modeled distributed, so that's very important. The assumption is that it's normally distributed. Are speeds actually normally distributed? Usually not. Right? So that's something just to be aware of, right? But doesn't have to be speeds. You can actually Levier segment locations too, and you'll get a nice clustering of things, right? But it's just a tool that takes a one-dimensional thing and it automatically identifies with some criteria, conservative sort of criteria, the number of segments in this thing. And it is implemented in the old ADE Habitat LT package. Great package. ADE, do you know what ADE stands for? Anybody? Nobody knows what ADE stands for? It's, so Clément Calange, he's French. It stands for Analyse des données écologiques, which is also ADE in Portuguese and Spanish and Italian, so all the old Romance languages. Ecological data analysis. Good package. So you have to deal with data types, but you learned how to do that, so I don't need to dwell on that. Both first passage time, Levier segmentation, old algorithms, that he wrote that up in 2006 or something, and it's all working great. Okay, so then I wrote this paper. It's part of my PhD work, was dealing with these animals. That's a northern fur seal in the Kuril Islands, north of Japan, south of Kamchatka. That has a lot of devices glued on its back. This is classic marine data. The sort of area-restricted search, kind of first passage time stuff, kind of doesn't really work very well on these data because they're irregular, and as we talked about this morning, that messes a lot of things up. They're very irregular. So these are like, you see the data, you can see there's big gaps between these data points, right? And so we don't know a priori what's going on. It's really hard to look at those data and be like, what is that behavioral structure in this data? It's in the ocean, the currents are moving, everything's moving, nothing stops, right? With anteater, the anteater stops, no problem. This never stops, right? So there's a female, it's feeding it just gave birth a couple weeks earlier, and then it's heading out to forage. And this is a week-long trip, but it's at sea. It comes back, really incredible. It comes back on this rookery has 20,000 pups. This female comes out and like orally finds its pup. Isn't that nice? Really incredible. That's where I did most of my field work in grad school, on these islands. Anyways, so this tool, this behavioral change point analysis, was supposed to be robust to irregular data, and it was supposed to be with no a priori assumptions, and it was like looking at what is the structure of this animal's movement. And we might revisit this data, okay? So, and then I do want to like talk about this because this is sort of like at the foundation of a lot of what these sorts of structural change point analyses come down to. So the way the BCPA, the original BCPA worked, right, which I don't think is the best tool actually for movement at all, but it worked for my purposes then. As I sort of parse, I take sort of a persistence velocity and a turning velocity, and that's just like between these locations, no matter what the time interval is, I'm taking the displacement times the cosine of that turning angle, and that cosine of the turning angle is sort of like the persistence, and the sine of the turning angle is kind of like a turning thing. And the reason I do that is because these things are more Gaussian looking. So at the time that was important to me. Now I realize it's not actually important at all. They tell you kind of two different things. But the fact that they're Gaussian means that I know that they're like, I know the distribution, and I know that there's some like autocorrelation that is dependent on just the time interval. It doesn't matter what the time interval is. There's only one intrinsic autocorrelation, which I would now write as the time scale, but back then I wrote it as autocorrelation, right? And then somehow these, the properties of these variables at some discrete time, according to the model, change, okay? And so this right here, so like this, something like this, all right? What is this? Does this look familiar to anybody? Like this sort of thing? It looks scary, but it's super important. So what is it? Does anybody have any idea what this L stands for? Likelihood. That is the likelihood, right? What about theta? What is theta in statistics speak? Theta, it's a bold-faced theta. Bold-faced means it contains multitudes. That theta is all the parameters. What are the parameters? Well, let's say we're talking about just the persistent speed. There's like a mean, there's a variance, and there's an autocorrelation. So there's 3 parameters, right? In one phase, and then the behavior changes, and there's 3 parameters in the next behavioral phase, and then there's that time point of that switch. So that's 7 parameters for one switch, okay? The likelihood says this is my distribution, so my statistical description, my probability, given those parameters of what the next location will be, right? And this is really just a normal distribution with a particular mean and variance. That's it. Just that variance also contains an autocorrelation. So this is normal distribution. This is a normal distribution with one set of parameters, a different set of parameters, right? And then this, the fact that there's 2 of them suggests that I'm doing one thing up to like data point little n, and then from data point little n plus 1 to the end, I'm doing a different thing. One behavioral change. What does that look like? Well, here's sort of like a time series. There's a shift in here. If you look closely, you can be like, okay, yeah, probably the shift is like somewhere in here, right? It's very easy to do something where it's impossible to see the difference, actually. If the thing that's changing is the autocorrelation, you can't see that. And the data are sparsely sampled. Some intervals are big, some are short, right? So this is kind of like what the data look like for one shift. And then what I do is I put a proposed change point here. I estimate all the parameters, left and right, the mean, the variance, and that autocorrelation on both sides, and then I get a likelihood. Or a likelihood. And then I just like move that little guy across, right? And at every step, I'm kind of left and right, okay? And then my likelihood, my total likelihood, so it's basically this thing, the log of this thing, which is what I'm plotting here, right? It will be peak where the model fits the data best, right? Where like my description, probabilistic description of this process has been, produces the highest value for these things. So there's no super, super crazy values which send it to 0, basically. All right? So that's that little bit. I'm showing this to you, even though I don't use the BCPA ever. I'm showing this to you because at the root, this process, this maximum likelihood estimation, first of all, 98% of the time that you're fitting a model, R is maximizing a likelihood, just so you know, right? So you've been maximizing likelihoods for a long time, right? That's happening underneath the hood, right? But you can make your own likelihood. If you can write down that likelihood, all you have to do is write it out and like have R find the maximum for you. It's very empowering to be able to write your own models. And I'm just going to show you, I'm going to show you multiple examples of this basic principle. Okay, but so back to the first seals, that's like the unit, the one single change point there. But you know, I don't know, maybe there's multiple change points. I don't know where those change points are. I can't just estimate, I don't want to just estimate one change point here because you know, there's a lot of things going on there. So this is where things get a little bit squishy. I have to like find a window, and I have to like come up with a step, and then I have to like charge through, and I have to like keep running this process, and I try to figure out what's changing and where it's changing, right? And I get a sort of complicated analysis. Okay, so that's basically the idea behind that particular approach. And again, it's designed for data that are highly irregular. Yes?
Wait, microphone. Can you pass it over?
So I think just going back a little bit in the example of the giant anteater that you showed, that's very different from this example. And you mentioned that in that situation, it's useful maybe to like segment, like separate when it's moving and when it's not.
Yeah.
But if I am trying to identify two behaviors, let's say moving and resting, how like how do I separate it when it's moving and how can I identify that it's resting or?
Yeah, we'll do that. We can do that. We'll
Okay,
probably do that
even-
with your
okay.
data even. I don't know if those aren't your data. Whose data were those? Do you know?
I don't know. Enriqueta was the name of the animal? I don't know.
Enriqueta,
But
yeah. I don't know.
Enriqueta, maybe
Aline
Gustavo?
Giroux had it.
I don't know. I never saw that name, but
I would probably, I mean, this is spoiler alert, but since you asked, I would just quickly fit a multi-state moment to HMM hidden Markov model, find the two states and use that and run with that for those data. They're pretty regular, and that would work great.
like
But we can talk about that. Okay, so the one thing that was sort of unsatisfying about that BCPA was that it's. Did you have a question, Alessandra? No. Yeah, what was unsatisfactory about it is that it wasn't actually a movement model, right? But then, so okay, learn more about movement models, learn more how to estimate them and fit them, like this correlated velocity model. And so this is a movement track of a whale, a bowhead whale in Western Greenland, in Disco Bay. And also, who the heck knows what it's doing or why? But it's obviously doing different things. And so if you're interested in that segmentation, so basically the exact same process. Find a window, find a step, but this time rather than estimate the mean, the variance, and that row for a persistence turning angle, I just estimate the correlated velocity movement model. So I'm actually estimating that time scale of autocorrelation. I'm estimating the speed of its swimming, and you can see that there's periods of higher swimming and lower swimming, right? So it's kind of nice, right? And like the patterns are kind of interesting. And then I also estimate whether it's like moving advectively or not, and when those advective movements are occurring or not. So we can, this is a little bit risky because I just barely got it to work, but we can try later if you want. It's gonna be like choose your own adventure a little bit. We can try to like do this to the first seal data, for example, and just see how it compares. And there's that kestrel. So again, this kestrel, Spain, southern Spain, flying around, and we can kind of like really break down its movements and be like, this is when it started, this is when it switched from one model to a different model. So in this paper, and there's a package that does, I just never got it up on CRAN, but it's on GitHub, and you should be able to install it. We kind of gave it a test run this morning, which guarantees nothing, but we'll try. Yeah. I mean, probably for your N reader, this is what you should do. We can also do this. This is just a recap, exactly what I talked about at length with Morales and his multi-state random walks. Hidden Markov movement modeling, multi-state random walk, fitting a multi-state random walk. And just one thing I want to point out here is that he fit multiple models here. And these are like state transitions. He fit a 3-state model, for example, right? A 2-state model with some predictors, which tends to be a little bit more consistent, and then just a totally independent 2-state model. All sorts of different things that kind of produce different outputs. But you can fit those. And this has been done, or a version of this is done a lot. It's really very, very common. And rightly so. Right, and just to give one example that I was a little bit involved in. So my postdoc now, Nikki, when she was a PhD student, she worked on sea turtles. And I just wanted to bring this up because this is basically kind of the output of her multi-state random walk, where she had 3 states. But it's not just the way we analyze these data. There's like these locations. The locations are kind of useful. They're irregular, like all marine data. But there's also dive data, independent dive data, right? So these are loggerhead turtles, and they have time depth recorders, and they sometimes do really deep dives when they're really foraging. They sometimes do lots of shallow dives. So we have the number of dives and the depth of dives, and we have all the parameters that we normally have, like the mean and like the turning angle, the step lengths and the turning angle, all that stuff. Then we also have the number of dives per day is another parameter, and we know that that's a Poisson distribution. And then we have the depth of the dives, which is another distribution, and we can put all of that together and we can get even better inference, right? And so we can really narrow down to like multiple states. So again, kind of the point of that whole exercise is really, or just the reason I bring it up is that you can do, turning angles and step lengths, but you can also, if you're willing to just go ahead and get into the code a little bit, the more information you have about your creature, the better for doing this, right? Now, an important note, a really key note, and like the reason, for example, there's a couple reasons why this is useless for my first eels, for example. One is that this really needs regular data, right? So if you're going to do this, you need to like regularize your data or just work on something terrestrial or data and like have good data. The other issue is that what are these 2 states? Like that's a very a priori thing, that there's just 2 states, right? And that doesn't really make a lot of sense maybe in other contexts, right? Or it's like a strong a priori assumption. So you have to know these are the assumptions, yet you know that this is what you're modeling. So in that review paper that I wrote with a bunch of friends, Chloe was on that. She helped a lot. I just compared. And this is really highly pedagogical, right? So I simulate a process where the speed is slow, the speed is medium, the speed is fast, and the speed is slow again, okay? And then I apply these 4 tools, okay? All right? It says, can I pick out the true behavioral changes, which I simulated, okay? So if the speed is changing, well, the first passage time actually works pretty well because it's like, okay, well, it was there, and it left, and then it was there, right? So first passage time did fine. I mean, it can't, maybe you can even pick out a difference here too, if you zoom in, okay? The Bayesian partitioning, which just tells you how many phases of different means and variances you have, nailed it. That's what it's made for. It's made for speeds, right? The behavioral change point analysis, well, it was a little bit fussier. It's like trying all sorts of like other stuff, but basically it also caught the main patterns here. And here's a multi-state random walk, a 2-state and a 3-state, right? I'll say it caught the 2 easy phases, but it didn't really catch a change in the middle, right? Instead, it kind of threw in a bunch of little phases on the ends, okay? So it sort of did, we'll say this is like A+, this is like, B, B minus, right? Now, what if what's changing is not the speed, but the tortuosity, or like the time scale of autocorrelation? So here, the speed is pretty much always constant, but I can create a movement that has kind of the same speed. It's just highly tortuous, less tortuous, very untortuous, and then more tortuous, right? So now I've like manipulated the autocorrelation. Well, as soon as I do that, then the model, which estimates speeds, changes in speeds, obviously fails, right? But it's going to fail, right? The first passage time, well, it kind of, my BCPA, I can design it for my little BCPA because the BCPA estimates those three things. I mean, it estimates that autocorrelation. It tells me, oh, the autocorrelation changed here, right? And it found it. And then the multi-state random walk does so-so. Okay? But I can also create a movement. This is not hard, and this is not crazy unbiological, where like the steps are totally correlated, but there's a biased attraction here, and then there's a biased attraction here. And like the switch of that, the biases switch, right? So it's like attracted to this location, it's attracted to this location, it's attracted to this location, it's attracted to that location, right? And if I do that, then everything fails. Because this is estimating speeds, right? And like step lengths, but the step lengths are all the same, and the turning angles are all kind of random, right? There's no bias in here. Now you can fit an HMM with bias and like attraction, but if you don't, you miss that completely. My BCPA is helpless, right? That, the thing that estimates changes in speeds is helpless because the speeds don't change. And it's actually the first passage time, like the most simple little but that contains space, right? So this tool contains space in it. It says, am I hanging around an actual location? And none of these contain space in that way. So again, you just have to know what you're doing and what you want when you're picking those tools. So that was sort of like a message I really wanted to get through there, okay? Now I'm just going to give a few examples of, I wouldn't call this segmentation necessarily, but if I have to call it segmentation, I'd call it targeted segmentation. And really, just a few cases where there's very particular behaviors that I'm interested in. Very particular behaviors. And I want to find them in the movement data. Not just find them, but find out when, find out where, and maybe a probability of them happening, right? So one thing, I work a lot, on caribou. Caribou migrate, sort of. A lot of animals shift their ranges. So migration and range shifts are something that are of interest to me. Calving or parturition, or for your bird people, your egg laying, I guess, incubating, whatever it is the birds do. Dispersal events, also very important, okay? So basically, sort of model-based estimation of behavioral change points that have a particular meaning, right? And again, this is sort of a little bit to show what you can do. So here, for example, there's a Marche RPAC. It's pronounced Marche, okay? It's not pronounced Marcher. It's pronounced Marche. Very important. Migration and range change estimation R. The idea here is, what's the model? Well, the model is that I have one movement behavior, and then I shift, and then I have another movement behavior, and that movement behavior is spatially constrained. It's going to be an OU, it's going to be an OUF, it's going to be one of those models, right? Or even a white noise data model. And then I'm going to have a transition, and I'm going to have a new one, right? And why was this useful? These are data from roe deer in the Italian Alps. And roe deer, like up here. Like you see this guy here? So I was asked about NSD, why do you square the displacement? So one issue with NSD is that, it's fine for a bird that migrates 3,000 kilometers. That roe deer seasonally migrates like 3.5 kilometers, right? Now it sounds funny, but in the Alps, 3.5 kilometers can mean a lot in the Dolomites, right? There's a totally different environment that it goes to in the winter and in the summer, and it has its reasons, right? It's just not a very big migration. And so if you try to do an NSD on movement like that, then it's super, 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 super sensitive to your initial starting point. Everything depends on the initial starting point, the whole thing, right? And so if your initial starting point is like in its summer range, but like closer to the winter range just a little bit, then you're not going to get a migration. If it's over here, then you're going to get some weird behavior, right? So this approach sort of like takes care of that, and it estimates actual timing. It estimates, what are the parameters now? We have like the area, we have whatever these OUF parameters, and then we have the time and the duration of that migration. And because there's a model and because there's a likelihood, I can just maximize it and find it. And because it's a model, so it's good for identifying subtle shifts. I can estimate parameters with confidence intervals, so like maybe normal people maybe don't care about that, but anybody that wants to do inference or estimation, it's always like, well, how precise is the estimate? That's like the question that inferential statistics is about. Chris will never provide an estimate without a confidence interval, ever. And then you can, because it's a statistical thing, a likelihood-based thing, you can like ask hypothesis questions. Like, was this a significant shift? Was there a stopover? And like, where was that stopover and when? And also, did it return to the same location? Like, here's a migration, it went up, it came down, right? And so, I mean, you don't maybe need a statistical test to say it came back to the same place, but if you want one, it's there. I worked this out, had a paper, fitted some data, made a tool, made an R package. It works pretty okay. And then I was like tasked with estimating the migrations timing of thousands of caribou, right? Thousands. It's this monster data set. And caribou are, I've learned in my years of working with them, are like, they do not understand how they're supposed to behave at all. Right? And so there's no way that I'm just going to like go through and manually like estimate these migration shifts, right? And I don't need to. Maybe I don't care about the individual caribou. Like for the caribou, what's important is how these migrations are shifting across these herds, how they're shifting across years, right? Across a big range. So this is, I'm just like kind of pointing out that sometimes it's maybe more useful to have a hierarchical model, right? We have a population level model. I want to know when the herd picks up and goes. So now I have a model where there's like, I don't care about the details of all these little ranges. I don't even care about the details of when the individual starts migrating. I kind of want to fit a model where there's like a mean and a standard deviation in that migration timing, where there's like a range of ranges, right? Kind of a mean, a standard deviation. I can develop like a range there. And I can fit that. Sort of a hierarchical model. And you know, that looks kind of like this. So these are from data, you know, a bunch of caribou. This is where they're wintering. And then this is where they calve, right? And I can estimate the herd level migration. So to do that, I used, I wrote a hierarchical model in Stan. So it's Bayesian, but the point is that the question was at the herd level. I didn't really care about the individual. The individual was like not manageable. So sometimes maybe some of your data is like really, what is the population doing? And if that's your question, then you should consider a hierarchical model. When we say hierarchical model, it sounds like a scary word, but it really just means that like a mixed effects model, right? What's the random effect? Or the random effect, I just don't care about the individual. I know they're different. I don't care how each individual is different, so I'm going to take all that variation of the individuals and put that into one mean variance, basically. That's what it comes down to. So here, my timing, migration timing, is a normal distribution with a mean timing and a variance, right? And I wrote an R package to do this. A little bit insanely, but people wanted it. So we could try that. And then I was just, since we're in southern Germany, I'll just note that Wiebke Peters and Johanna Zinger, they work in Germany. They're German. And they asked if I could help them with the chamois. And this is like in southern Germany, in the German Alps. Can I also throw in, kind of do something like Marche, but also include the elevational gradient, right? And yeah, again, this could be really, really simple. The chamois don't move a lot. You know, they aren't that correlated. If you're asking a question on the scale of like an annual or seasonal migration, you don't need to worry about every single location every 20 minutes. You can just take one location a day if you want. It doesn't matter. It really doesn't matter, because that's not the question. The question isn't what it's doing here. It's when is it shifting, right? And then I can just, be like, okay, well, each of these in X, in Y, and in Z, I have some model, not a regressive model. That's good enough. And then I just, here's the likelihood, just estimate the parameters. And so this is what it looks like, right? So it was here, and it went up here. Okay, that helps. And just for a little more power in their inference about the migrations, the altitudinal migrations. Another thing that we are interested in is parturition times. This is my picture. This is not something, this is thankfully not collared. But mammals give birth, and I guess birds also give birth. When mammals give birth, they tend to stop. They tend to hang out for a while, give birth, and then they nurse for a little while. It takes a different amount of time depending on the species for the creature to wean, right? And so the movement behavior kind of changes in a very, very specific way, right? And so there's been sort of a couple of model-based approaches to kind of get at that. So I'll just show you how those work a little bit. So again, this is just movement rate. So and this is like kind of the original paper by Demars et al. Movement rate, you can see that if you look at movement rate, you can fit, or they fit 3 models to this movement rate. Just displacement per whatever the interval was. And you can see that there's like, it crashes, right? And then it kind of recovers. And they fit a model that sort of either nothing changed or it crashed and then slowly recovered. So that slow recovery is different than crashing and like immediately popping up. Because immediately popping up sort of suggests that the calf maybe didn't make it. And so the female caribou resumes its life. I will say from caribou that adult female survival really improves if their calf doesn't make it. It's costly. Also give birth. But anyways, this is extremely useful because you have animals that are collared, and I don't know if this is relevant to you guys, but a lot of animals that are collared in very remote places, it's very hard to like observe them give birth. We can't track them, but we have movement data. And the movement data maybe, with a tool like this, can let us know where, when, and whether this parturition event occurred. And that's obviously, for like a population level questions, again, hugely important. So that's also, there's a package that's not on CRAN, but that we have that can do some of that stuff. And again, fundamentally that tool, so the tool that Demars did, and then we kind of like refined it a little bit in this paper that looked at kind of continental-wide caribou parturition. It's all just likelihoods. I fit 3 models, I see which one has the lowest AIC, that's like the model, but I also use the likelihoods to find the time of calving and the time of recovery. Yes?
So the interpretation for these 3 plots is that only in this specific time, that for the first one there is no birth at all, like just in this specific time, and so on, like calf survival, and then how do you treat? You remove this part, this period.
We want to know when it happened and whether it happened. So this model just has 3 parameters, basically, maybe 2 parameters. That's it, right? So you fit it, and you get an AIC value. So the AIC, by the way, AICs, you're familiar with AICs. You use AICs because you're like, so you should know that AIC, what is AIC? What is AIC? Who can define AIC for me? Raise your hands, one at a time. I know everybody wants to tell me what AIC is. Can anybody? Go ahead. It's not like, this is not an ambiguous question. It's like what AIC equals.
As in, you want the formula?
Yeah.
I mean, I know it's based on likelihoods and attempting to balance the numbers of parameters versus how much information from the data you're capturing with those parameters.
This is a marker? Yeah, that is exactly right. That's an awful lot of words for a formula that is just AIC equals -2 log likelihood plus twice the number of parameters. Everything you said is in here, right? This is the likelihood, right? The negative log likelihood. Higher likelihood means better model, better fit. But the more the complicated, the more parameters you throw into a model, the better it's going to fit, always, right? And this is the penalty. And you want the lower AIC. So in this model, K is 2. In this model, K is 1, 2, 3, 4, 5, 6, maybe. Something like that. But the fit's going to be better, obviously. And in this model, it has maybe the same amount of parameters as that model, but the fit's even better. And so of these, the lowest AIC by like 100 or more is this one, which kind of suggests that, okay, it had a calf and the calf died. So that's why it's so great there's so many reasons why it's great to have a likelihood, right? You can maximize it and estimate a parameter, but then you can also compare models with that likelihood. So that's how that works. So yeah, we don't do any cutting. We just want to know. And we can throw hundreds of animals, 1,000 animals. We threw 1,000 animals into this algorithm, 1,000 females, across 30 years, across most of North America, right? And we're like, okay, well, this is probably where they gave birth, and this is the probability they gave birth. And you could at that scale, you could be like, oh, there's trends, there's patterns, there's a lot of interesting patterns. We can relate that then to, I know no context, but we could relate that to to wind and to snow and to temperatures and to like previous summer conditions, all sorts of things that we care about. But this is just a change point analysis. That works basically in the same way. And then just one more example. I really like this one. This is like totally not ready for prime time, but we had, you don't have this bit, so I was involved in a wolf project in Finland for many years, and a lot of tracked wolves, and some wolves, a wolf can just be born in its territory, live its whole life in its territory, right, and then die. But some wolves eventually, actually a good number, disperse. So you have like your natal territory, and then this wolf is like, I want to reproduce, mom and dad look really healthy, only two can, that's the way wolves work, right? So I'm just going to strike out into the world and then find a new territory. And we were, the paper that this was part of really had to do with their behaviors before and during and after, and had to do with boldness and, interactions with roads and houses and all this stuff. And I had an undergraduate that was kind of helping me with this at Maryland. And, I was like, well, it's obvious when they disperse. We just we just say they disperse. And he was like, no, it's not good. I can't write this down. I need a tool that tells me when they dispersed, right? And he was just like really good for him, right? He was like, eyeball isn't good enough, right? So I was like, fine. We'll define dispersal as a shift between having range resident behavior and range on-resident behavior, and then back to range resident behavior. That's the definition of dispersal. That's a good definition. It really vibes with what is dispersal, right? Marchais doesn't work for this because Marchais sort of assumes sort of a pretty straight line. So it just didn't work, right? But this transition, so it's its own transition. We have a model here. This gets a likelihood, this gets a likelihood, this gets a likelihood. Find the change points, you're done. Right? And this is what it looks like, start and dispersal settling. And that's actually very, very useful for a lot of people who are really interested in dispersal and multiple dispersals, especially in disease dynamics. So people in the US are very concerned about chronic wasting disease in particular among white-tailed deer, for example, and they really want tools to identify when dispersal is occurring in deer. And then I worked with another Brazilian, Bernardo, who's in, do you know Bernardo? Anyways, he works on puma, and he has this nice, also. Dispersal is just very important, very fundamental, right? It's not migration. It's not really, it's kind of a range shift, but it's a very particular kind of range shift, and it's hard to do. Wolves are easy because they're so territorial and so clear, but anyways. So those are just some examples.
Yeah, no, sorry.
Is there a question? Yes.
Yeah. I think then we can also apply that to any translocation. Like what happens, for example, with leopards. Leopards are dumped in a place, and they have this behavior of searching, exploring, going away. Then actually we are interested in understanding when they settle. So we can use it the other way around.
Absolutely. Yeah. Right? But you're probably, I guess part of, maybe the larger point here is there's probably not going to be, as hard as some of us try to make tools that everyone can use, there's probably not necessarily going to be the thing that already exists. There wasn't a thing that existed for Nikki's turtles, so we had to make one. She had to learn how to make one, and she did it. And it was better. And it was better that way because she understood the model. She created that box herself. And that, if you want to this process of translocation and learning and settling and figuring out how to settle, then you might have to write your own model for that. But it'll look something like this. You just have to find the right movement model. Yeah, Anna.
Yeah, I was just wondering because migrating animals, of course, they do this multiple times, but they shift, they have the range resident behavior, and then they don't have it, and then they have it again.
Yeah.
And of course, they do that every year, probably. But would this method also work if this behavior is repeated? Because maybe also in dispersal events, maybe it's not as straightforward as this example. So an animal has its parental range, leaves, has another range, and then it's no, don't like it here. And then leaves and goes to another one. So it could be, so maybe it's not the final one. Does this method or is it only if the start and the end, once the start and once the end, and then it identifies it? Or is it, just wondering.
That's a super great question, right? And that's the reality is that animals, most are not this nice. And this package that we sort of started working on with Bernardo, the idea was actually to just embrace the fact that it's complicated, that it's hard, and just to kind of bundle together a suite of tools that help explore that. Now, if you know how many times, there's there might be a hierarchy where you're I can cluster the movement data, for example, step one, cluster the movements. How many real clusters do I have? Are they robust clusters? There's lots of clustering tools, spatial clustering tools, even first passage time. It's probably good for that, right? Use that, and then you have a number of clusters, and if you want, you can identify your times of starting and ending of those clusters if you know how many there are. You just have to know how many times, how many little T's there are in here, if you want to use this particular tool. But there might be other tools. And I'll also say that here, again, we kind of having a movement model, but maybe you don't need a movement model. Maybe you don't need a movement model per se. You just want to know when it's doing what it's doing. For the parturition, this isn't a movement model. This is just when did it give birth and did it give birth. So, okay. I propose we take another break. But then after we come back, I have this you choose. I think I would like to show you, because this example is very tidy and really good to go, how to fit this Memento HMM, just how easy it is now to fit a multi-state random walk. It's a very useful thing to do with some data. So I have the data and the code up on that folder. But after that, we could try to use Smooth to do this behavioral change points for continuous time movement models. We could try to play with Marche. If you really want, we could. I could try to do this hierarchical migration model just so you get a feel for how some of these things work. So it's a little bit up to you. I don't think we can do all of it, but I would like to do this one and then maybe pick one of these two. Yeah.
Yeah, just two previous examples. Do you really believe the model does better than you just looking at the data and choosing? What's the point of automating this?
The point is that there's hundreds of animals.
Okay. But say if it is more
Or
muddled.
thousands. For here there's 50.
Okay, but yeah, if it's more muddled than this, then do you think the model would actually do better than you looking at the tracks at recovering patterns that are actually
no.
biologically meaningful?
I didn't want to do this, but Tim really insisted. Yeah, it's not about better or not better, but if it's reliable and consistent and you can automate it over a lot of individuals. That's the issue. So wildlife managers in the United States of America with these they really have thousands of these white-tailed deer collared, and they can't give a dispersal probability estimate, right? They just can't do it, right? Or a dispersal kernel even. They kind of do crudely a little bit, but no one's going to sit down. I'm not going to sit down with every freaking white-tailed deer they tagged in southern Minnesota, and assess this. So it's for that automation, right? I did briefly start looking at individual caribou. Yeah. So that's the main advantage. But yeah, right, that's the question. Do you need this? Maybe you do, maybe you don't. I don't know. It's not for me to answer. Okay. Yeah. Yes.
Just another question. When do we know, like, if it's better to treat like all the animals together or individuals?
Whether to do a hierarchical model or not? Yeah, I mean, most of these analyses, most of these kind of track analyses are pretty individual. The only time I've ever done something for a population was that hierarchical migration estimation for the caribou. I think it's when you have too many, or like you just don't care about the individual question. It depends on the question, I guess. Yeah. Yeah, it depends on the question and how much data you have and how hard it is to do. Yeah. But there's something I have to say. It was kind of nice that the hierarchical model. I mean, it really just like it sort of like tamed all the it allowed the caribou to do their own thing. You know, in a way that was very nice. I thought. Like it really gave really nice, robust, consistent estimates. You know, and individually, it would have just been really, really, really hard to do that. There isn't maybe even necessarily enough data to do that individually, especially with the older years. So it just like let them do their thing, and I like that a lot. With that, you know, there's just a massive data set. But yeah, but this is an example. This and also the Marché package itself is an example of where you would use these OUF, OU type models as a piece of a segmentation. Any other questions? Well, let me just ask you guys then. I mean, would you rather do this smooth thing or this Marché thing, or you want to do both? Smooth? All right. Okay. I'll try to make sure it works while you're on break. Wow, okay. Back in the saddle. Ready to go? All right, let's do this. I just wanted to point one thing out, just sort of a plug. I'm sort of trying to fill a gap. It seems like there's kind of a gap for like really applied practical like movement analysis material in one place. So I'm trying to write this kind of like book. For now, it's just like this online thing called Techniques and Concepts of Human Ecology with Applications in R. And it's a little bit messy, but you know, it has a structure. It has like an introduction and links and like stuff. Yeah, you know, a moving bison, all sorts of cool stuff. Foundation, you know, I don't know. Maybe it's a little bit like this AniMove course. You know, some stuff about why do we need spatial statistics. There's like some things are kind of developed. Let me just show off the segmentation chapter because there's a lot of this too, right? So there's the segmentation chapter. It has nothing, but it has headers. So there's a start. But anyways, it's something I'm kind of working on. Some things are a little bit more developed, like some of the spatial data. But there's a sort of a question one of the students, I'm sorry I don't know your name, asked about, you know, where can we get maybe like sort of a step-by-step, because you read a paper and the statistical material is often very dense. It's not that easy to read methods-based papers, but you guys are looking for appropriate methods for your tools, and so this is the intent is for it to be very like practical, kind of pedagogical with examples and stuff, and also open projects if anybody wants to contribute chapters, by all means. So, anyways, I'll somehow get this link to you. Yeah.
Would you be willing to share your notes from your presentations?
Yeah. You mean like the slides?
Your slides?
Yeah. I think they'll be, one of them is now in there. Yeah,
Oh, great.
Yeah, I'll dump them in there. Yeah. Okay, so now if you would please go to that shared drive, wherever it is. Where is it? I don't know where it is. Where is it? Here we go. Yeah, so under, I don't know, maybe the organization will change, but for now, under movement models and segmentation, this is just what I did. Probably we should maybe name them by date or order or something. But in here, we're gonna start with the, oh yeah, here's like the first presentation I gave is here in PDF format. It doesn't have the animations. I'd have to host those online somehow. But I download this elk reg data and this lab HMM. Let's fit a hidden Markov model first. And we'll just give that a shot. I'll give you a minute to, and myself a minute to find that. Let's see, just. So just give me a minute here. HMM, yeah, so this, yeah, let's do this one first. So there's, oh yeah, I also wanted to point out that I'm sorry I don't have nearly as many words here as Anna and Martina had explaining things, but that said, this particular one came out of, like I said, I was in Brazil, and like the first week in Brazil, I taught this sort of like it was, you know, it's like this, but I was alone with my postdoc. There were just two of us trying to get through a lot of material in 1 week. This particular lab, so there's like some code here. The lab that we're doing right now is basically the one that comes, there's some changes, but it's basically this multi-state random walk. So here there's a lot of words and pictures and a little more detail if you need that. So again, I will share that link. But for now, let's just focus on this. Can you see that okay? Should I make it bigger? Everyone's okay? So let's see. I need to the source allocation. Okay. So let's load the data. This data consists of, it's the bare minimum of movement data, which is good. ID, we have some animals in here, multiple elk, individuals, date, longitude, latitude. Now, one thing I will say, the raw data, and this is data from the Yahatinda ranch in Banff, that was collected by Mark Hebelwhite, if you know the name. So it's kind of, and it's an open access data set that's on MoveBank. And there are lots of interesting behaviors there and lots of data, very long-term interesting data set, which Mark has just done a wonderful job of keeping available. So if you wanted it from like, the raw data is out there. Now, this particular data object, because we're going to fit an HMM model, is regularized, okay? And in order to regularize it, there's like a whole other like step of fitting modeling that I'm not going to talk about at all. So we're just going to accept the fact that it's regular data, 2-hour locations, okay, of these elk. All right, so this little bit of code, I'm picking out one model, or one animal, but if you want, I suggest you try doing this with someone else. So we have a couple elk to choose from. So pick one of these elk, YL 96, 78, 77, 73, 29, 25, or GP2. They're all good for this purpose, I think, but every animal is individual and unique. But just to show you what this one looks like here. So this is all stuff you've done. We subsetted for this individual, turned it into a simple feature, transformed it. Why did we transform it? So the latitudes and the longitudes can be turned into something whose distances make sense, right? So it's transformed into these metric units. I love the simple feature package. It's really wonderful. You have no idea how good you have it compared to some of us that still remember the SP package. But one thing that annoys the heck out of me is that as soon as you turn something into a simple feature, it actually like hides the coordinates. So I often have this little line here that's just like this. I often have this, the C bind, give me the coordinates back. I just want my coordinates because I like dealing with the data, the actual data. And the simple feature, bundles it all up in there. You can always get them out. But this way, I know that I have columns X and Y. So now all that was just to transform this thing into, we don't need any of this for now. So now I have ID, date, X and Y, metrics, the distances all make sense, and then the geometry, in case we want it. For those of you that have map view working, you can, of course, just map view your elk, right? Map view, my elk, UTM. What? Oh, I see, because I sort of undid the, well, anyways. You can check out where it is. It's always fun, if you can. If you can't, then that stinks. So yeah, so there's this particular elk. Maybe you guys have a different elk. Here we are in the province of Alberta in the Canadian Rockies. Very mountainous area, and a lot of their movements are really constrained by these valleys and this sort of seasonal migration. Okay, so we're going to be looking at this seasonal migration a little bit here. A little bit, and not just the seasonal migration. Okay. Everyone's with me? This is the package, Moment2HMM. Does a very nice, very efficient job of estimating these models. So I have that installed and ready. And like all of these packages, just like AD, Habitat, just like Move and CTMM, there's a function here. It's called prep data, which is not very descriptive. So you have to know that we're in Moment2HMM world, which is going to do the same thing all these packages do. Go ahead and run that. What? Oh yeah, because I have to rerun this line. So what does prep do? Somebody tell me, how is my elk HMM prep different than my elk HMM? Or my elk UTM? What's in there? Yes? Yeah, step lengths and angles. That's nice. Okay. So again, we're going to fit a multi-state random walk. So it really is going to use this and this. Now, I'll just note, step lengths and angles, great to have. A lot of packages use them. I also use step lengths and turning angles as needed. But in what I like doing, this is just something you have to be aware of, is like, well, what is this step? What is this step? The step is from here to here, right? And I almost always like having the step that brought me to a place, right? So like my steps, if I was like to have steps, or sometimes I do have steps, they often come. So that'll be like an NA, an NA, and an NA here. Because I like thinking about how I got to a place. That's where I'm getting out of the place. Anyways, let's just be aware of that. Okay, now, this is not long and this is not too complicated. We're going to fit a two-stage model. Do I have a... Okay, well, later. I almost always have this scan track function, which lets me look at how this movement changes in time. Let's just go ahead and see that, because it's important. Here, it's very, very important. We can just pick one coordinate for now, but let's just go like, so I'll do something like this often. With my elk UTM, just plot date, and just say X. equals O. Plot margins 2 large. Okay. Oh, battery's dying on my mouse. No. All right. Where's my plot? Yeah. Oh gosh. Live coding is the best. All right. There's the plot. Okay. So see, this is just in the x-coordinate that in time. So it was here in April through May, June, something, and then it shifted somewhere else, and then kind of came back. So it's summered in high elevations, basically. Okay, so that's pretty clear pattern there. But we want to get a little bit more detail. So we're going to start with a two-step model, okay? And you have to very often, so the computer's going to do a lot of computation for you. It's going to like maximize its likelihoods. It's going to like get the fits, right? But you do need to seed it with something, right? And this is actually doesn't work in a Bayesian way. So this is just really a maximum likelihood maximizer of this model, which is terrific. Just makes it a lot faster. We're going to have two states, 1 and 2. And we need to provide some sort of initial values for these, right? And this is where you have to look at your data if you're like doing this to your own animals, right? And we're going to be like, okay, so my mean step length is going to be, for the one state is going to be very low. It's kind of like my initial guess. And for the second one is going to be much larger, right? So I'm going to have like a sedentary and like a kind of like what Morales had, encamped and transient or something, whatever he called it. And then my standard deviations, I need some standard deviations around that mean. So this is kind of like, these are the parameters that are going to go into this distribution for step lengths, but it's in terms of means and standard deviations and not shapes and scales, which is better, a little more intuitive. And then we have angle concentration. So we're going to have a low concentration, so low speed, low concentration prior, basically. That's not really a prior, it's just like the initial estimate, the initial starting point for looking. The closer the initial guess is, the easier it is to find something. And then for the second state, we're going to have a higher row. Okay? So that's pretty clear. These are just our initial guesses for our 3 parameters for 2 states. That's what that line does. Okay, boom, boom, boom. Okay, and then you have to do a little bit of other prep. So this is because there's different ways to like parameterize things. We're going to have a gamma distribution. I don't know what the exact options are. You can read the documentation from Memento HMM. It's quite good. But gamma, wrap Cauchy. All right, Delverpi Cauchy, gamma. And then those are our distribution. We have a distribution list. And then we have to create our sort of our null parameter object. It's also a list. The list has to have the name, step, and angle. Although Memento HMM can fit other things that don't necessarily use those two. All right? So everybody's clear on what we did so far? State names. Oh yeah, resident transit. Okay, resident transit. The function is fit HMM. Easy peasy. So run that. If you haven't already, this must be a named list. Come back. Oh, yes. All right. So, did you fit the model? You ran the line? Okay. So, you can print the fit. What does it tell us? Okay. So, you should be able to interpret all of this output. A pretty big chunk of, quantitative ecology in R, or just applied ecology and data analysis in R, is interpreting output that people thought is the format that you should see things in. So we have step parameters. We have a resident state where the mean step, so step here, we regularize the data. We know what that means. That's the mean displacement in 2 hours. So 2 hours. In 2 hours, there's a state where it moved 128 meters on average. every 2 hours, which is, an elk can do a lot more than that. And there's another state where it moves 600 meters on average in that 2-hour interval, right? And then we have some standard deviations, which are typically going to be quite big. Then we fixed the mean at 0. We're not interested in like persistent rotation, just always do that. And then we have this resident state where the concentration is actually, this is a little bit weird for us, it's lower. Oh yeah, no, that's what we want. We expect the concentration to be lower for the resident state than for the transit state, okay? And then we have these progression for the transition probabilities. Now I'll say moment to HMM, we have no context here, but if you want to, you could make those transition probabilities depend on a covariate easily using formula notation in R in that fit HMM command. Okay, so that's exciting actually. So there's our transition probability matrix, simple matrix, initial distribution, okay? So that's the print output. Now we can also plot this thing. Right? And so now we assess, okay, we fit the model bit. Is it a good fit? Is it telling us anything useful? All right? So let's just look at the output of this thing. So if you do plot mallocation on fit, it'll ask you to, it'll give you several plots. These are the plots that it thinks are useful for you to assess this model. Okay? Here's the fitted distribution, the gamma distribution for the 2 states, transit, resident, and total. Okay, so we have this, like, okay, it's good. The transit, we like that the blue has a larger step length. We hit enter again. Here we have the wrapped distribution. If I were designing this package, I would have made it a Rose diagram. But it doesn't matter too much here. It's very clear that that transitory state has a higher concentration parameter. So we can interpret that. And this one has an almost uniform parameter. And then one more. Now this is where the rubber kind of hits the road a little bit. We have the states kind of mapped onto the actual trajectory. I'm a big fan of base plot in R, so shout out to Brett McClintock and company who I happen to know for also using base plotting for their things. Anyways, there it is. There's the, now, do you like this or do you not like this? Did this capture, I mean, it depends what you want to capture, right? But what do you think of this? Somebody give me a comment on this particular partitioning. Yes?
I wouldn't say it made a lot of ecological sense to have so much transit where also it's like it's being resident, so maybe it needs more than 2 states for it to work.
I like that. Very well put. It is not really picking out the transitory state away from, it's adding a lot, it's letting there be a lot of transitional states in these very clearly range resident phases, right? So let us try 3 states, right? And so that's basically what Garcia says. I will say this is an important function and actually concept is Viterbi. Viterbi is basically an algorithm that's going to output the most likely states for the data. So you need that if you want that prediction. I mean, that's what it's running underneath here under the plot. But if you actually want those states, you want to get those out. And right here, so this is its best guess of what state it's in at every moment. You can add that to your, oops, sorry. Here I'm just going to give you like an example of how I like to visualize the output of the segmentation, right? Here, this little bit of code is just showing us where those states are inside of in time, right? So most of the transitions are blue, but there's just a lot of blue and orange inside of these clearly resident states. Okay. Just a quick note. This is like, I'd call this a scan track. This layout, if you're using base R, I guess you can do this in ggplot too, but I don't know how. This layout, cbind, C1, 1, 2, 3, those guys, on the top everywhere, that means that my layout is going to be broken up into, this is 1, this is 2, this is 3. This is like a matrix. That's how you control these layouts. So that 1, 1, 2, 3, allows my 3 plots to be laid out in this way. Okay. You can also do this in map view. I'm not going to bother. Let's just jump into the meat of things. What happens when we do as, I'm sorry, what's your name? Eloise. As Eloise suggested, which is try 3 states. Same sort of thing, right? Except now we need an initial guess for all 3 states. Mean 1, 2, 3, standard deviation 1, 2, 3, row 1, row 2, row 3. Throw those all in there. And, this is a pretty well-documented package, too, I should say. So there's lots of vignettes and like online stuff. I'm going to call this resident slow, transit, and resident fast. And so notice I just threw in some numbers that are kind of intermediate between these two here. Okay, same distributions. Here are my null parameters of this list. I need to have a list that looks like this, right? These are my parameters for the steps and for the angles, and I just run the exact same command. This is a new fit, 3-state. Should be pretty fast. Should have done this by now. Okay, done. All right. Okay, let's just take a quick look at the numbers. All right, well, that's good. It estimated a bunch of numbers. And indeed, we have a resident mean step, which is quite low, 100 meters. We're down from our 200 meters down to 100 meters. And this like intermediate thing, which is like 500 meters. And then our transit thing, which is up to 2 kilometers per 2 hours. So it really did separate these things quite nicely. Standard deviations. And then we also have kind of what we expect, the lowest concentration for this ultra-resident thing. There's something intermediate here, and then there's like very directed movement in that transit phase. And so we can extract those states. And yeah, if you want to plot. Well, let's just go straight to this thing. And we'll see if this satisfies Eloise's expectations a little better. So now what you see, and this is kind of fun, right? So now what you see is that these really long movements have really been picked out as that 3rd phase, or as that 2nd phase. And we have real structure in here, real structure in those resident phases, it's alternating between red and orange. So let's go ahead, the second little bit of code here, and you can kind of study how it looks. In the second bit of code, I'm going to do the same thing, but I'm going to just focus on the first month, April. Okay? I just want to, I'm going to zoom in, right? And what we see here is that the orange is like the super resident thing, right? So there's like little chunks of orange, and then there's like some red connecting these little orange states internally. So that's kind of satisfactory. And then, oh yeah, by the way, now that we have this state prediction, we can see how much time it's spending in all these states. So it's spending, according to this modeled fit, about equal time in these two basically resident states. And like really, there's just these really dramatic movements that are really picked out really nicely. I think really nicely, actually. For this data, it did a great job for these transient movements. But anyways, I want to be like, okay, well, what are these states? And this is just a very simple little example of, just a trivial initial analysis. What if we look at these states against time of day? So in case you don't know, here's like a table of this state against time of day. So we can just see what state it's in, different times of day. And you do a little bar plot, give it the same 3 colors. And this is kind of nice, because what you see here is that, again, the orange is the super resident. It's really not moving very much. The red is it's really transitioning. You can see that it does most of its transitioning. Assuming, this is a big assumption, that the time zone is correct in your data. And it's local, not GMT, which happens. So watch out for that, because you will get very wrong inferences if you're working in Alaska and it's in GMT time. All right, day and night will be just like that. Anyways, assuming that the time zone is correct, you can see a very clear daily pattern in the probability, basically, or the amount of time that this elk spends in these states. Right? So that's a nice, tidy analysis. It worked out pretty well for this particular animal. Did you get it to work? Did anybody do a different elk?
It didn't work out well for the one.
Yeah, so, and that'll happen. Obviously, I didn't do, actually, I'm happy, I didn't really cherry pick. This is just like the first one I got, and I got this, so I was happy. But it might have to, you should look at the data, you should see what's going on, try different initial values. Yeah?
So would you do these? Do you generally do these individually, or just group all the movements of all the elks?
Right.
Because that elk apparently didn't work well with those parameters.
Yeah, exactly. Yeah. So I don't know. I mean, I guess I would. I mean, this is a tool for analyzing this particular elk. I think the general approach is to try some individually, really understand what's going on. If things don't work, try to figure out why they're not working. I'm not sure whether it's possible that, because people have talked about this forever, including, so again, I know Brett McClintock, who wrote this package, about population level inference, but I think you might be able to do that with Memento HMM even now. So then we're talking about a hierarchical model, a mixed effects model. But if you can't with this package, then you can if you write out an MCMC sampler yourself.
You can with Move HMM for sure, with the population.
Okay.
Yeah, and HMM TMD also.
Yeah. So there's. Yeah. So I think that field is like has matured. It was always like the pipe dream, but I think now you can do that in the population level. But this helped a lot. I mean, I think just to like even figure out that, oh, maybe a 3-state model is better than a 2-state model. It's good at this individual level exploration. Yeah.
How you can set a limit to the number of different states you can, tell apart from your movement data? So, what is the number of different states you can?
I think so.
What is the limit? So.
Yeah, I don't know that I've ever seen a 4-state model, frankly. It's getting hard to separate. And we're estimating a full transition probability matrix. So for every new state that you add, it scales as that squared. So you have to then estimate, not 6 parameters like we did here, but 12.
Okay.
But I also don't think that it makes that much sense, unless you have a really, really good reason. Now, as with anything, it really depends how much data you have. Now, maybe you have in here also, like maybe with the dive, you have like other dimensions of data, altitudinal data or something else. But we also, I'll just say that if you use covariates, then you can also like absorb more variation. And if they're the correct covariates, then the models tend to fit even better and stuff like that.
So it could be that there are also, for some individuals, there are not all the full stages. So maybe there could be just 2, and on the other individual it could be 4, and so on.
Yeah, and you can use weighted AIC or DIC to compare these models. Actually, here there might even be just a straight likelihood. Yeah. That was in Move HMM. Yeah.
It allows you to compare the AICs of the different models. So, for example, you could just keep adding states and it may work better, but then you can say it might be that 4-state looks nice, but actually AIC with 3 states is better. So it does. I don't know for this one, but I know for Move HMM, you can compare your different models to see which has the lowest AIC to deal with just not adding models. I think the recommendations are also like how many states make, again, ecological sense, which is always quite frustrating. So if you have your organism, maybe it has lots of different types of behaviors that might show up, but you may be like, it's actually just really basic and it just walks and sleeps. And then you know that adding more might not actually help with the ecological side, even if your model looks really shiny when you're doing it?
Yeah.
That wasn't my question, but my actual question was, so I have data which is regular in theory. I mentioned it earlier too, but it's regular in theory, but there's these big, big gaps. And so I can't interpolate or do anything because they vanish for days, months, sometimes at a time, but come back. And one way I was trying to play with HMM models is if I took the bursts that were regular and then put them all in to the HM model, but I don't know if I'm breaking something if I do that. So it works in the sense that all the little snippets it gets, it sort of treats like individual tracks. And they're all regular, so it meets that assumption. But I don't know if what I can infer when I do that, or if I'm messing around with it a bit too much to have, because it will be like multiple tracks with the same ID of the animal. But is that fine? Is it not? I don't know.
Yeah, it's totally fine. I mean, your model is that no matter what the burst is, because you're not letting the burst be different, like behaviorally, the animal's in one of your states and it has some transition probability of switching between those states. The information that goes in is you can't use like a turning angle if you're like missing 3 days of data, right? So, and you're taking that into account. But yeah, it's totally fine. You're fitting that model for the data. So it's not fatal. That said, I'm not going to actually like 100% vouch for like what is actually how it's dealing with that. But it's not. I know that that's not a problem because all it's doing is, I mean, it's just taking the state. It's taking the steps and turning angles that it has. So in principle, it shouldn't be a problem. There's no reason it would be a problem. And you're not breaking anything. You're just using all the data. What you shouldn't do is like use the gaps as if it were a real step. That'll mess everything up. Yeah. I will just say it's also like, why are you doing this? What do you want to know? One thing that I've done, and this is in the context of like basically a resource selection or step selection type model function, is like rather than like use every single location for this model, this is for caribou again. Caribou, they're either moving or they're not moving, right? So I just like blindly, and this was nice because again, lots of freaking animals. I just blindly fit a 2-state HMM to all of the data, right? And like kind of checked, it looked pretty good. And then what I classified as movement, right, was like moving from one like transitory state to another transitory state, because I think the resources that are more important to animals in general are that resources where they're foraging, right, where they're like moving a little bit less. And the transitory, step selection, maybe there's some patterns there, right, but they care less about the resources when they're trying to get someplace. And sure enough, that was kind of like, when you compared that, you said, okay, the selection was stronger for like where I'm foraging. So like I would just use this basically to be like, I'm only interested in the orange parts. I want to know what is the resource selection for this orange behavior, which is like the camped out behavior. And then I really don't care about the the other ones, but I can compare them too. I can do all of that. So kind of like that 2-step thing. So that was nice because I have an estimate of the state. Any other questions? Yeah.
This is just a question on what you said. If you isolate a specific state and run something like a resource selection function for that particular state, are you eliminating all the other data from, like, do you end up with just a really gappy track with only the selected state that you want, or how does that work?
But I don't want to analyze the track.
Okay.
The track is like the raw data that comes off the device. That's not what I want to analyze. I want to ask a question about where are they foraging and what are they selecting for when they forage. So yeah, I'm throwing out everything that doesn't matter.
Okay.
Because I don't, that's not that particular question. Yeah, you're throwing out data, but like it's not, you don't have to be like, it's not, I'm kind of using this as a guide to like narrow my question. But there's tools, right? And again, statistics is like, this is not the answer to anything, right? This is not the truth. This is a model. It's a fitted model, right? And it helps guide me. It helps show me that there's some structures, some patterns, for like my actual question, right? And I can also use statistics to assess. Okay, I assessed like just the strength, the sheer predictive power of the resource selection function for those foraging states compared to the transitory states, and there's just more selection, right? There's a bigger distortion between the use and availability for when I trimmed out that orange thing for the caribou. So that was great. So that was like, okay, so I'm getting closer to something that I'm actually interested in. And what they're interested in is like, what is the quality? What is landscape quality, and how do you do range management? These are very applied questions. There's a question back there.
Can you talk about model validation in this case? I mean, I know you can compare maybe field observations with the Gurarie outputs, but in case you don't have those, is there any other way to confirm, like,
In case you don't have what?
observations of behavior that you can really compare?
Yeah, so I guess the short answer for a question like that is always like cross-validation, right? So you can, although it is a little bit tricky because you have to know the states or the things that you're validating against. Yeah, that's actually, I don't know. I don't actually have a quick answer for that as far as validation. It's like, what are you validating against? I mean, that's the issues of this is you're inferring a process that you can't observe directly. You're inferring this transitions between these discrete states. So validation sort of assumes that you can like make predictions and then like assess. I mean, one thing you could do potentially is if you had covariates in there, right? You had covariates in there, you could see how well those covariates do at predicting states, which you then like estimate without, maybe. I haven't really seen that done that way. But there's no validation. You just have to be like, okay, this is the model.
Okay, so you can really say in what level of confidence you really separated those behaviors.
No, but you can certainly. I mean, it's certainly just you know, this is again where you have to like trust yourself and your ability to like interpret your ecology, right? I mean, I can look at this and I can say, and I can look at the estimates, and I can say, like, if it fits really terribly, right, then like there'll be a lot of overlap here, right? I have confidence intervals maybe around some of these estimates too. I can use that as a guide, you know. I use some other statistics. Yeah.
Okay.
So, and really, you know, I think this picture is a pretty good validation.
But maybe I would also say that oftentimes with segmentation, we are anyway trying to pick up a pattern that we see by eye often. And so when you then look at the pattern and you apply let's say you look at a bunch of individuals, you apply these models, and then you look at other individuals and you see how well is it doing. And I think you can trust your eyes in seeing, can I pick up that pattern? Then whether that pattern means exactly what you think the animal is doing, this is a different thing and you're not in the brain of the animal. But at least you can probably say by eye, am I picking up the pattern that I meant to pick up? Or what would you say? You also wanted to say something, Andrew? No.
Oh, yeah. One of my PhD chat. Ellie, we did this with acoustic validation of segmentation.
Right, okay, yes, if you have individual use for validation, yeah, good point. We did do that. So if you have independent validation of behavioral states, so in there, so in Edward's PhD, I don't know if you want to talk about it, but basically fish eating bats in the Sea of Cortez. So that's Edward from the Sea of Cortez. They have acoustic devices and GPS devices, high resolution GPS devices. And so Edward has a nice paper from his PhD that's on different behavioral segmentation tools, and then just seeing how much they lined up with the calls, which you know are related to foraging. Kind of know that they're related to foraging. Like, you know, they're related to like getting all the bats excited about, because they're fishing at night with their like little backwards feet. But, yeah. Anyways, it's a crazy behavior, and everything's moving. They're all moving. The water's moving. You know, but when something gets found, they aggregate. So you know a little bit when they're. So we use that as a validation. You're doing some validation thing with camera collars on caribou, right? Aren't you?
Yeah, well, it's pretty much done now. I'll have to send it to you.
Yeah. So, right, so there's validation there where, which is actually very useful stuff where, you know, there's camera collars so you can see where these are caribou in this case, that when they're foraging, when they're moving, when they're engaging in different behaviors.
I'll say the little caveat with that is like, you're fitting an H&M on like 2-hour fixed rails. And the caribou can switch between behaviors that
Yeah.
that timestamp. So if you validate that, like, it will say like, oh, well, the caribou is generally resting in that time, but like in the video, it could very well be moving. So like that's where like I think the validation isn't so good right now. Is what I found. Like I'm guessing like for caribou, you need like 5-minute fix rate. You fit an HMM on that to actually have like really good validation with the like 10-second videos.
I mean, it depends.
But it just like depends. Like yeah, you have different scale. If you have like a 1 point per day, then you won't get at like fine scale foraging. It's just
Yeah, but so like I don't think there's a way. I don't think just fundamentally there's no way to just only use movement data to validate itself when it comes to this hidden Markov stuff. There is absolutely for resource selection, step selection, you know, habitat use, all sorts of things like that. But using pure movement data to validate itself is not possible. So you need some sort of other piece of information. But yeah, as Benjamin said, so like, you know, that it's not that easy. Even with camera collars reveal everything, but there's not that much information. Like they run for like 5 minutes per hour or something like that. Is that right?
what? Like the video is only the video is 10 seconds at every location, and it's like 20-minute fixed rates. So
okay.
yeah,
that's,
so
okay.
you
That's
get
even
a
different. That's different
10-second
than what I
video
was
every
doing.
20 minutes.
Yeah. So, right. So there's like maybe if it's in the generally foraging state, you're somewhat more likely to be eating, but you know they're not constantly eating, right? They're like switching back and forth. And so like that fine scale behaviors are just they're not matched to the scale of the movement data in general. But generally, if like you know I'm not in the you know I'm not like just booking here. Like this is 1 day, right?
Yeah.
Right.
We really compared with field observations, and the match was poor. So.
Oh. Yeah.
Because they might be just in an area where they graze, but actually they're walking while the person actually took the note. And yeah, then the validation process was really unconvincing.
Please use the microphone.
Oh, sorry.
Yeah.
If it's like a little comment, then maybe it's okay, but if it's longer,
Yeah.
people that will watch the videos.
But yeah, so you had field validations, you had external validations. That's what you need is external validation, but you can't use move intrinsically. Should we try the smooth thing? Give that a shot? Okay, so to do that, I don't actually think I have that particular line of code. But if you just maybe search, maybe GitHub Smooth. This guy, Gurarie Smooth. And so again, this package is online. You're going to have to install it off of, it's on GitHub. It's on CRAN. So it's kind of, GitHub is like the development version, I guess, but this has just never been published. It's ready to publish, sort of, but it can be hard to pass all the checks. Anyways, try running that line of code. I'm really, really curious to see how well this works for.
So you all have installed it when you installed the AniMove package. Just saying. So you don't have to install it again unless you change something.
I changed things this morning.
Change something. Okay, then go ahead.
Sorry. I wanted to give you the best possible version.
We'll challenge the internet.
Okay. So hopefully that all works. Well, so there's an AniMove package that just includes all these packages somehow, or?
Yeah, we just ask the tutors what are they going to talk about, and then we just include. It's basically a package that installs all the packages that the other tutors are going to use. And we call the GitHub repository, but that was 2 days ago. No, yesterday?
Yeah. I mean, maybe it won't make too much of a difference for this particular thing, but yeah. I did change the way it outputs. I like better the graphical output. So let's see, where's that thing? So that might be called, Lab Smooth BCPA. Okay. And is the first seal data, you might want to load the first seal data too. I uploaded that, didn't I? Okay. Let me just, I don't know where it is now. Oh yeah, Here it is. There we go. First seals. Okay. So I have to say these are all data. Nobody really should care too much about them, but I didn't actually get explicit permission from whoever the theoretical data owner is. So please don't circulate this wider. Okay. I mean, it's not a big deal, but they're a little bit old, but just a fight. Okay. So I'll give you a little time, load the first seal data, some packages. And I'm just going to talk about, the Smooth package. And so one thing I'll note is that I really did put a lot of effort into the vignette for this thing. So if you go vignette Smooth, that's like, oh yeah, I need a, I actually don't have I don't actually have the vignette built with the vignette. But anyways. But yeah, here's a version of it. Yeah, if you install it, try installing it with build vignettes. Hopefully it'll work.
It seems to be hanging on the vignette.
With an error, or is it just? Yeah, it took a few minutes. Yeah, it's because it's doing things. It's writing the vignette.
So much effort into it.
It's writing the vignette. Here's the vignette. Here's what it looks like roughly. I talk about, just in the vignette, I talk at length about some of these different models. There's some equations in here, like how to simulate these different movements. So there's like different ways to do all this sorts of stuff. How do you estimate these parameters? But then, I think what you're most interested in, or what we're most interested in really, is near the end where we do this behavioral segmentation. Okay? So this has a lot of words. We can walk through it. We're running a little bit short on time. So we're just going to try to do this. So I'll just walk you through the code here. This is completely unannotated. But again, there's a whole vignette. Is it still building?
It's on my computer.
Okay. Does anybody not have Smooth installed? It's totally okay not to have it installed. Okay. And you loaded the first seals? Try map viewing the first seals so you know where they are. So here we are on the Kuril Islands. Really amazing part of the world. So just, while I'm reminiscing, that picture of the sea lion I took while I lived on this island for 2 months in a little hut with one person. That's in Sifra, and then I lived on, it's a big volcano. Oh yeah, look at this. There's like volcanoes inside of crater lakes. There's like hot springs all around. It's really insane, really beautiful. Anyways, this right here, you can't even, you can barely see them. These are like these, this right here, these are these lavushki. Lavushki is, this is like the very tip of an extinct volcano. So it's just barely the crater. Like the highest elevation is like 20 meters or something. And like on this island right here, there's like 50,000 fur seals, something reproducing, right? So it's like really an intense environment. Pretty amazing. And so out of that, out of here, this first seal goes out, and these are like 7 trips that it took. So much like with the, what does this do? Much like with the elk, pick a trip, 1, 2, 3, 4, 5, 6, 7. Here they all are, sort of ggplotted using GMSF, which is nice. I like that. Just see how it goes. So here's one trip. Okay, and so I don't like that. Well, anyways. Okay. So, yeah, Martino's right that generally if one way to validate is just to see if things look like you want them to look. But with these data, it's really hard to know what you want them to look like, right? So, she left, she did some stuff, and she came back, right? And but it was constant movement, and there's big gaps and just highly irregular sampling. I will say there's kind of an issue that I sort of went under the rug, and that is the fact that the regularity of the sampling also sort of depends on the behavior a little bit. It's like you get less data if she's foraging more, things like that. But anyways, that's the track. Okay, so this is all a little bit, this is more than you need necessarily. Estimate UCVM is a function. Estimate UCVM is a function which will just estimate the parameters of this correlated velocity model. The unbiased one. There's no rotation, no nothing. And for the method, you have options with methods, but I think maybe the the velocity likelihood is a good one. Another alternative is this crawl. Anyways, doesn't matter. These are the estimates. So this is just, I talked about the models. I said we can estimate them. I didn't talk in detail about how you estimate them, except to say that there is a likelihood. You can write down the likelihood. And basically, we have here two parameters, tau and nu. This is on average for the whole track. Just one set of parameters with confidence intervals. That nu is basically the average speed of that movement in meters per minute. And this is like the autocorrelation in the time scale in minutes in the velocity. This is a velocity autocorrelation model. Okay, so that's what estimate UCVM does, right? And it also maybe, let's see, provides, I forget now. No, it just provides estimates, okay. So, and like I said, when you actually do the whole change point analysis, you're just going to be like estimating a lot of these things. Now, this other function, estimate RACVM, allows you to estimate sort of the four options that I have, some of which are a little bit, a little bit esoteric. And so here now, these are the estimates of like, okay, what about an advective rotation? This is not an advective rotational movement. It's kind of clear that it's not. But there's like estimates for this, like the rotation is omega, for the the mean squared velocity, advective components, the tau. All these things get estimated. But importantly, it also does a little comparison here and tells you, well, actually, just stick with the uncorrelated correlated velocity model. It has the lowest AIC, and you don't need all this other crazy crap. And it's clear that you don't, right? This is not, there's nothing helical around it. But I just want to show that it does that. You can ignore this stuff, just ignore this stuff. I just wanted to confirm that these multiple methods, yeah, anyways. There'll be some errors, but again, that's not important. I just wanted to confirm that some of these, I don't know what that's, there's an error there. Give similar estimates. But here's the sweep, okay? So here comes the sweep. This is the exciting stuff, right? So it's kind of like 3 stages to this, like, okay, what are the multiple behaviors that this is moving between? That's kind of the question. So this is the sweep. It starts with a sweep. It can probably just take a simple feature in here at this point. The parameters here, so it's not just like the number, the original BCPA was just like how many data points I have. Here I'm going to go with like hours, 12-hour window size, a 12-hour window size. So that means that I'm going to like just assess, I'm just going to try to get candidate change points where's like the most likely change point in every 12-hour window, and I'm going to sweep that window every 2 hours through the data. Okay? If I don't have a lot of data, so be it. If I have a lot, all the better. Right? But my question, I want sub-daily resolution potential changes. Okay? And then this model argument, again, all the details are in the vignette. That model argument just tells me I don't want any of the advective stuff. Just UCVM. Give me a nice, unbiased, correlated velocity movement. Use the crawl method. All right? So it's going to like crank through. It's going to crank through. So again, what it's doing that little thing where it's just finding the most likely change point and estimating the model on either side of that change point for each of these windows. Okay, so now I'm going to just clear that out. Okay, so I get this output. All right. So basically, every color here is another window. And in each window, I have like, some most likely change point. And this is the likelihood score across all those windows. It's a complete mess. Right? There's just a lot of crap going on in there. But what I do then, so there's like a couple things I want to do now. I want to pick out the peaks, the most likely peaks, these behavioral changes. And then I want to assess what's actually going on in those. And do I keep them or do I not keep them? So it's kind of like 2 stages. So first I get these candidate change points. Now it gives me a little warning here. Some of your partitions are very small, probably too small. You might consider reclustering the change points. Okay, well, fine. I don't know how you decided that, even though I was the one that decided that. But anyways, it doesn't matter too much. You get, so these are like these are like the change points where there's like the most clustering around those change points, basically, right? So I'm kind of thinned things down to 7 change points, for example, right? And then there's this final step here, well, I guess almost final step, where I assess whether those change points are significant individually. So now, this kind of like this last stage is going to come here. I'm going to look at the behavior before and after this change point and see is this a significant change point or not. And that might clean up the change points a little bit more. So that should be pretty quick. And then, if that worked for you, I'll do like the second one. I'm going to create my phase list. And this phase list basically says, so after I did some thinning, and maybe this is too radical of a thinning. Maybe I should like tweak some of these parameters a little bit. It's telling me that there's, okay, here's 5 different phases. Here's when the phase started, here's when it ended, and here's the model. And these are the point estimates of these different parameters. And then finally, this is the thing that I was working on this morning. I can make a little phase list plot where I'm sort of like breaking it down into these like 5 different behaviors. And basically, what you see here is that, and this is maybe, again, this is a little bit too coarse, and like other times I've done it, there's like more changes. But what you kind of learn from this particular partitioning is that, first of all, there's this like, okay, we're swimming away and we're swimming back, and those have the highest root means square speed. Right? This eta is basically like the speed of movement. So it's like the highest speed of movement is like leaving and coming back. And there's like this yellow phase, which even though it's quite long, but this was a phase which had the least correlated and the kind of generally the slowest movements compared to some of the other phases. Now, again, I could do this analysis. I'm not sure why it came out this way. Other times it is a little bit.
Some of us got 10 phases for that same data set, others got 7.
Yeah, so it should be pretty consistent. It kind of depends which of these 2 that this cluster width actually has quite a bit of an impact. I think 6 hours maybe is too big. Let's ignore that warning, because again, I have no idea where it came from. I think it had to do with the clustering there. Yeah, so that maybe looks a little bit more exciting. Yeah. So it's finicky, but that's how it works. And actually, this also included this, it also sort of said that it shifted between, I'm missing the other ones, but when it shifted between advective, and a lot of the times the advective model is the one that pops out. And this tells you whether it's advective east or west, right? Yeah, so that's pretty much how it looks. You can see that it went south first, and then, yeah, came home coming south, went out going west, came home going east. You kind of knew that. But then it kind of breaks down the, again, that time scale, it's like the scales are a little bit screwed up there, but it's most intensive, even though it doesn't look it at all. It's doing the most intensive sort of movements in here and the foraging in here. And that actually makes sense when you know a little bit about the bathymetry there and where the upholdings are. So that's how it works. It is as a completely sort of, I would say minimally supervised, minimal assumption tool, it can be an interesting way to look at your data. So, and it really doesn't care how your data are sampled. And it'll give you speeds and things like that. So you asked for it, that's what you got. Thank you very much.